Má to být live nebo ne?
Live.
No. Můžu do toho USBčka dát?
Určitě.
Dobrý, já se to jenom poradím.
Já tady budu muset možná nějak přepínat, který z těch mikrofonů to je, ne?
Musíte...
Ne, to máte jako, to máš jako jeden výstup dohromady z toho. Ty mikrofony pořád jdou oba.
Akorát musíte přepnout na to zařízení, no?
Právě, no. To znamená,
želio nebo něco takového.
No. Si to neumíte poradit. Tady musím si tam tu... Nevím, to jestli to bude rozbit. Jsem zapomněl YouTube. Tyhle ty zdroje toho zvukového signálu, že?
No, to je ten Jerry. Chvilku, teď už jsem měl...
Jo,
to je nový mikrofon. To musí být, ne.
Jenom mikrofon.
Ne.
Reproduktory by měly být to HDMI. Já to ještě nemám nastavené.
Jo, ještě nám dáme. To nevidí. A HDMI je kde?
Zezadu.
Vidím.
Ještě ho tam dát. Děkuju. Tak to by to...
Já jsem zapnul projektory. To jsem zapnul, koukám, jenom plátno, to je málo. Ty projektory.
Tak se ještě musí odmutovat ten zvuk, co jsem si udělal.
To udělal, jo? Projektory oba.
Jo, nechci to udělat. Jo. To je zmáčkou to člověk.
Je to pro.
Tak co, jak jsme na tom?
Ještě bliká.
Tohle mám na YouTube ten zpožděný, akorát teďka nevím. Normálně se mi to potom. No, ani moc snad ne, spíš...
Potřebujete myšku nebo něco?
Asi ne, to není tak různý. Tady mám ještě přes YouTube to a vlastně nevím, jaká je ta adresa toho YouTube, to vylám, kde se to nahrává. Ono to není určený, aby se na to lidi dívali, jo, ale jenom pro
Nedá se to přes tohle poslat odkaz?
Dobře.
Když měl třeba pošleš e-mailem, a ho zkusím tady. To už hledáš nějakou zradu, jo?
Já nehledám zradu, ale vypadá to, že jsou nastavený to redakce na takhle. Teď můžeš vybrat z optího projektu, to půjde, jestli to nebo pro nás. No to je připojení místo.
Jo, jasně, aby to
ano, zelené to si.
Jo, už to dáme.
Nebo použiju a to ještě to. Ale to jsme ne, to se nepoužívá, to musím vidět, na tebe široký. Jo, to je třeba jak to. No. Jo, to je lepší, než to je udělám. Já jsem teď nějak udělal, že to se to nezahádění. Spoustu jiných věcí, jak jsem se připojil na ten e-mail.
Takhle to tady jakoby vidím, no.
Jo, slyšíš něco?
Jinou tepu, ano. No, ale jak nastavit tohle ještě?
No to je asi nastavený.
Někdo
asi to hovoří,
jinak
slyšíš to?
Jde z toho zvuk, no.
Jo.
Pokud to nebude hovořit, tak nevíš.
A zkusil by si to samý na tom?
Raz, dva, tři.
Raz, dva, tři. Takže tady bude to moc nebliká.
Ten link jsme poslali včera, no, zkusím.
Můžu zastílit, to je s tím mikrofon v ruce, ten mám v ruce. Hej, hej, hej. Dobrý den, to se stáhne. Já si budu říct strany, protože takhle, jak mám hlavou dolů, tak to vždycky pletu. Jo, takže to nechceme asi nahlas, aby to bylo aspoň do těch zelených. Raz, dva, tři, můžeme ještě trochu. No, teďka by to mělo být už na počítači dobře slyšet.
Tak, a pokud si v místnosti někdo pustí ten Zoom a dá si to nahlas, tak se to zavazbí. A začne to pískat. Protože z toho jeho speakeru to půjde na náš
Já to
mikrovky.
chápu.
No to bude zpožděný.
No, oni no teďka ten YouTube je zpožděný, ten jako ne, ale Zoom do Zoomu to je rychlý.
Zoom do
To by
Zoomu je-
mohla vazbit.
Takže jim musím říct, aby nepouštěl si ten...
Mikrofon by měl být rychlejší.
Ne, mikrofon mají, ale to je na váš mikrofon.
Jo,
Oni nesmějí si pustit
zvuk, no.
zvuk na tom svým počítači.
No, to byste nezněl blbě, to je potom to mluvil stokrát, to chci vyloučit, no.
No přesně tak, ale hlavně by se to vazbilo na váš mikrofon.
Jasně, no, jako já si nejsem úplně jistý,
Ale jak já jim neumím zakázat, aby si pustili zvuk.
No pustě, ale já si myslím, že to nebude taky vazby, jak říká Martin, že to má...
to můžeme zkusit,
citlivost
tak
určitou.
Tak já zkusím, no teďka to máme tady
Je
přes
to-
mobil, no, ale to
Ale tak to je slabý, no.
To je slabý, a je to zpožděný, ale on ten mikrofon,
Ty už jsi na Zoomu nebo
Jo,
na
na,
YouTube?
na Zoomu.
Teď už je i na Zoomu.
jo, ten mikrofon bude jenom taková blízké, že to není jako nějaký, ty počítačový, ty berou fakt ty kondenzátory z dálky, takže
Ok.
ten by tam měla být menší šance pro zpětnou vazbu. A ještě tam máme potlačové zpětný vazby, teda zázemí nějaký.
Dobře, no, každopádně já jim řeknu, aby si teda nezapínali reproduktory, aby si vypli reproduktory na svém počítači, jakoby, jo? To je
Určitě.
nejistější asi, jo? Protože kdyby tam náhodou měl puštěný ten Zoom, že si toho nevšimli, že se na to klikli, pak si zavřou tu záložku, takže ani nevědí, že ten Zoom mají puštěný, že jo? Protože když jim řeknu, vypněte si Zoom, tak oni ani nevědí, že třeba
No, jasně.
běží, jakoby, jo?
Já poprosím taky na e-mail ty odkazy, jak na Zoom na ten YouTube, jak to mohl nějak nahrávat ještě po naší.
OK. Ale tady já to už budu nahrávat dvakrát teda, jo, takže, ale na Zoom byste už měl mít, nebo už byste měl být včerejška, jakoby, jo, přišlo to
Jo,
e-mailem,
ano, to
jo. A teďka ještě, když tak ten YouTube, ale
A ještě potom musíme ten...
by to šlo z toho počítače. Tím se to možná víc zalozví ještě, no. Počkej, my to nemáme ještě tady, teď jsme tady nastavili.
Já si myslím, že musíte nastavit ten vstup jako ten jelly.
No určitě.
To jsme dali, ne? Jelly?
Ne,
to má
reproduktory by měly být
místo,
naopak
naopak.
to HDMIčko, to jsme čekali to HDMI.
Takže tady ne, jo?
Ne, tady to HDMI, protože hraje se do, vlastně ono je to DVX, Intel Display Audio, no, display,
Tohle to?
ano, display, protože my hrajeme do bedem posluchárny.
OK.
Tak. A teďka v tom Zoomu se to nastavuje.
Tady v tom, nebo tady v tom.
Ne.
Asi tady v
To
tom.
je asi jedno ten nějaký nastavení někde. Ono ty, u toho mikrofonu jsem se to dá listovat i tady, když se dá špička u audia,
Jo, tak tady se před...
tak tady se to dá na ty jelly.
Teďka mi tam dal
Ne?
Tenhle ten, jo?
A teďka by to měli přímo z toho mikrofonu, jo, se tam mi zasílil ten signál, že předtím on to bral vlastně tím mikrofonem notebooku z těch beden. Teďka by to mělo znít jak v rádiu, pokud bylo dobře mluvit.
Tenhle ten.
A teďka by to měli přímo z toho mikrofonu, jo, se tam mi zasílil ten signál, že předtím on to bral vlastně tím mikrofonem notebooku z těch beden. By to mělo znít jak v rádiu, pokud bylo dobře mluvit. A teďka by to měli přímo z toho mikrofonu, jo, se tam mi zasílil ten signál, že předtím on to bral vlastně tím mikrofonem notebooku.
Neslyším. La 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 la. La 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 la. Ladies and gentlemen, dear colleagues, welcome. My name is Zdeněk Hanzálek, and this is CIIRC Annual Colloquium on Research Results. La la la, la 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 la. Nejhorší je držet ten mikrofon přesně před tou pusou, protože když ho dá člověk takhle, tak to slyšet pak není, no. Jo, 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 jo. Dobře.
Jedna, dva, tři. Jedna, dva.
Trololo, trololo. Tak budete to chtít připojit přes ten Zoom, nebo to budete ode mě? Zkusím to přes Zoom. No. Tak já bych poprosil, aby se přihlásili vedoucí oddělení, vedoucí skupin a lidé ze sněmu, aby Chyb mohl dát takové hodnotící archy, nebo poprosil bych tady Marcelku, jestli by jim to rozdala. Takže kdo jste vedoucí oddělení, nebo vedoucí skupiny, nebo jste ze sněmu, tak se prosím vás přihlašte. Tak se přihlašte, ať vám to může dát. Jo? Hodnotíme jako ve škole, to znamená známko. Yes, we are evaluating like in a Czech school, not in German school. So grade 1 is the best and grade 5 is the worst. And we are evaluating in 2 categories. One is like presentation and the second one is the content, right? So for example, presenter, me will have 2 grades. If it's me, then 1 and 1, right? And that's clear, right? And more important is if you have some observation, you can write it just simply below the title of the presentation. And then those sheets will be given to respective departments, groups, and then they can do whatever they want with that, right? Do you understand what I meant? Is it okay? Okay, so thank you for coming. Můžeme začít, Vladimír, teda? Jo. So, ladies and gentlemen, welcome. My name is Zdeněk Hanzálek and I am happy to introduce CIIRC Annual Colloquium on Research Results. And now let me ask Vladimír Mařík to tell us something about CIIRC research strategy.
Thank you, Zdeněk. Thank you for the preparatory activities. I hope this workshop, which is organized each year in January, will help to understand what we are doing and will support, let's say, communication, cooperation between different teams in CIIRC and outside of CIIRC. As a matter of fact, we will celebrate 12th anniversary very soon. And we have started from the scratch. Today, we have got quite a strong research institute with more than 300 employees, with many teams, with many projects being solved. And projects is something what is very important to all of us because we are receiving, let's say, 3-4% of our funding from the government, from the institutional funding. And the rest of the funding depends on our European projects, on funding from national projects, and of course, also on industrial projects, direct contracts with industry. So at the very beginning, we have decided to have a broad scope of activities from excellent research up to industrial applications. And we follow this track all the time. And today we can say that we are able to act in the whole broad spectrum of activities. We have got participation in European Centers of Excellence. This represents the excellence part. We have got some ERC grants and ERC-CZ grants. That's also something what distinguishes us from different units at the Czech Technical University. We have got a lot of Horizon and EU projects in general, which are partially focused on new technology, partially focused on industrial deployment or on industrial needs. And we have built, and last year we have started with European Digital Innovation Hub, which together with the National Center for Industry 4.0 represents the most important body for know-how transfer from our academic space into the industry. So the whole ecosystem is built. And as a matter of fact, the most important project which helped us a lot was the RICAI project and is still RICAI project, which helped us with the equipment, which helped us to pay tenure track positions, 4 of them, which helped us to develop infrastructure. This year, or in February next year, RECAIP will be ended, and we need to find some replacement for this backbone project. And from this follows the most important task for us this year. That means to prepare application for a project which is called Large Research Infrastructure. That's a project which is funded by Czech government using European structural funds, usually lasts 6 to 8 years. And this is the project which might successfully replace funding coming from RECAIP, and which might also, let's say, continue in maintenance of our equipment, upgrade, because in our area, upgrade is also very important, which could help also to educate and prepare new researchers. So we have to concentrate our efforts to preparation of a very good proposal, because competition will be very high. And we need to collect information which is not only in the field of excellent papers, but we would need to see and to collect all the information concerning industrial deployment. Because there are many solutions here which are already in production lines, for instance, in Lego, at Airbus, there are solutions, Škoda and others. What? Okay. We have got, let's say, solution which is used in small but very efficient power plant. You will see the information about it. Control algorithms were delivered from CIIRC. So there are many industrial applications, but the management of the institute is not aware of all of them. Moreover, our equipment is deployed by some small companies, bigger companies. This should be also reported. And we will collect this information starting next week, because time is running. We will use this information about your papers, about your cooperation with industry, with healthcare institutions, with, I don't know, transportation institutions. We will collect them also for the purposes of institutional review. After 5 years, our institute will pass review in the last week of June. We will pass review by international panelists. There will be a group of experts from around the world coming and evaluating whether we are still excellent. As you remember, 5 years ago, we were recognized as excellent body, one of 3 at the Czech Technical University. I hope we will keep this stamp of excellence also for forthcoming 5 years. It's very important for, let's say, our position in the Czech research space, for our reputation inside the country and abroad. So we will collect this information. We will ask you also to participate in, let's say, preparing the report for the panelists, and simply to cooperate with us in gathering the information. We feel we are not fully aware of all the activities. There are many of them, some of them are small, because small company wants something for 20,000 crowns. But we need to have everything under control to report it to our governmental authorities. And the other issue, please, there are many solutions, but just a few patents, just a few licensed pieces of software, few, if some, if any, let's say, protected solutions, užitný vzor. This is also very important part of our output, which will be evaluated as well in large research infrastructure, but also in our evaluation. So please, if you have a good piece of software, try to protect it. Just report it as a protected piece of software. If you have something what might be patented, please patent it and start to think about it and do it right now, because we will be evaluated in June, and in July we have to submit our proposal for large research infrastructure. Join these two activities together, try to think it over, what might be patented, what might be protected, and which kind of cooperation with industry you were engaged in, you could report it. Moreover, the last wish of mine, we need to keep the track of excellence. That means we need to go for ERC projects. ERC projects is something what is a real stamp of excellence, which is recognized in this way. And there are several teams here, I would like to say many teams here, which might try to apply for ERC grant. Maybe the first trial will be not successful, but that's experience which might be reused next year. Please be so kind and think it over again. Who thinks there is opportunity for our team to apply? Let's try to do so. And there are already people who were awarded by ERC grant who are ready to help. Josef, am I right? Yeah. Josef, am I right? So these are experience, and we need to go this way. This is what I wanted to say at the very beginning. I'm looking forward to your presentations. I'm looking forward which kind of new pieces of knowledge and which kind of solutions were achieved last year. Thank you very much for preparing this, for participating in this workshop, and I hope it will be successful as usual. Thank you very much.
Paváš to introduce his department.
So, robotic machine perception, we are the first in the list today. I'm proud of the results which were achieved last year. You will see them. And there is a new thing. We have a new head of robotic perception group, which is Karla Stepanova, and she will take over now.
Hello, everyone. I would like to very quickly introduce Robotic Perception Group and the results we achieved in 2024. And as was heard, in CIIRC, we are interested also in the solutions which extend beyond the scientific results. So I just want to give you an overview of some of the results which we actually in 2024 delivered to end users. And thanks to Thatcher and Edich projects, and those range from applications which connect machine learning and perception, and also robotic solutions. So, for example, we develop automated pallet jack to supply pallets to bricklaying robot, which is actually was showcased in Night of Scientists and will culminate this year. And also long-term effort of Vláďa Smutný, which was supported by Thatcher and Edich, resulted this year in the final application of robot motion planning for welding of plastic tanks in cooperation with several industry partners. In 2024, we had also several scientific results, and for presentation today, we selected two of them, which are main work of our two PhD students who are finishing their PhD this year, and it nicely summarizes what they actually achieved during their PhD. Gabriela Šejnová submitted her thesis already in December, and Ondra Holešovský will submit it this month, hopefully. So I hope you will enjoy their work, and floor is yours, Gabriela. Is there a pointer or?
Okay, good morning. My name is Gabriela Šejnová, and today I would like to introduce our research on multimodal variational autoencoders, which was presented in October at CIIRC and which is also the main topic of my dissertation thesis. Multimodal variational autoencoders are neural network-based generative models that are able to learn some shared joint representation over multiple data inputs or modalities. So, for example, language with vision or action. And during inference, it's possible to omit some of these modalities on the input, and we can then generate one modality from the shared joint latent space based on the data inputs that are currently available. And also, since these are generative models, it's possible to also produce multiple output samples rather than just one solution, so we can have alternative solutions to the given problem. There are currently several state-of-the-art multimodal VAEs, but they have been mostly tested only on image and text data. And in our project, we wanted to see whether it's possible to apply these models also on robotics data or robotic manipulation task. So, and more specifically on the data side, it would be relatively easy to collect in the real world. So you can imagine raw camera images, natural language commands, and some robot motion trajectories where the robot performs the action. And so the goal was to systematically compare and evaluate the state-of-the-art models on this kind of data and perhaps find some possible improvements to this architecture. So we generated 36 synthetic data sets using a simulator. The data composed of raw camera images of the scene. We used a Franca Amica robot with two-finger gripper, which was controlled using end effector positions and binary values for gripper closing and opening. And we separated the data based on the scene complexity. So either there was only one object or one or two distractors. We also separated based on how many actions the model had to learn in parallel. So either it only learned one action, such as lifting, moving the object left or right, or it had to learn two actions at the same time or three actions. And we also varied the positional variability of the object and the positional variability of the robot, I mean the amount of the variability, and the length of the task that it had to learn. Here we should play an example of the data. Okay, so it's very quick. This is the number of represented actions, just single one or two or three at the same time. This is the distractors, one or two objects or just single object that need to be lifted. Here, the length of the task. So the longest task was picking the object and placing it into a drawer and closing it. And here's the positional variability. Yeah, it was quick. And so on this data, we compared three state-of-the-art multimodal VAEs, which differ in the way they learn the joint representation. So there's an overview of the methods. The other parts of the architecture were kept fixed to make it a fair comparison. And also we compared two reconstruction loss functions. The standard mean squared error was compared with the sigma VAE loss, which is a newly proposed method by Ripkin, which analytically computes the variance of the decoder distribution. And it showed promising results on single model VAEs, so we wanted to apply it to multimodal scenario. After training, we generated 500 testing trials for each data set, where the model was always given the camera image and the natural language command, and it had to produce the trajectory. And we passed the trajectory to the robot in simulator and observed whether it fulfilled the task. And the numbers here are the reported accuracies of how many times the robot fulfilled the task out of the 500 trials. As you can see, the sigma VAE loss function performed the same or better than the mean squared error in all of the cases, so that's quite a clear enhancement of the model's performance. The MVAE model is most robust to all the criteria that we observed, the positional variability, scene complexity, and also the task length. However, the accuracies for the more complex scenes with one or two distractors were always very low, which indicates that the mapping between the pixel space and Cartesian space of the robot is still quite a challenging task to be done in an unsupervised fashion for the model. So that should be our focus in the future research. And since this research, we also focused on developing transformer-based multimodal VAE, our own approach, which we compared on this data with the state-of-the-art. And that's also my other part of my dissertation. So that's all from me. Thank you.
Did you assess generalization of the approach to like new objects or new situations? Or how do you think about this?
Yeah, we are thinking about it. Of course, we had to search through many different variability of the model. We were looking for some functional scenario where the model had some optimal latent space size, and there are many parameters which we had to fine tune. We also altered the objects, but some broader study that actually really defines what is possible and not needs to be done yet, I think.
Hello, my name is Andrzej Holešovský, and I'm going to talk about our paper Moving Cable Segmentation Method and Dataset by me, Radoslav Škověra and Václav Hlaváč, published in the journal IEEE Robotics and Automation Letters. It addresses the following problem. Imagine there is a scene with complex tangled cable clutter. This problem is hard for perception or for cable segmentation or cable instance segmentation. Humans simplify this problem by grasping the cable of interest and moving it. This motion basically simplifies the perception. We follow a similar idea in this work to segment moving cables. We approach the problem by first recording a data set of moving cables. In this case, it's a yellow hose with ground truth, optical flow, and instance segmentation masks. We painted UV fluorescent cylindrical markers using a transparent paint on the hoses, and switched or alternately switched between UV lighting and white lighting. This enabled us to collect both or simultaneously collect images of both the fluorescent markers and the marker-free cables. We recorded multiple different cable configurations with multiple different motion types. When we had this data, we post-processed them to obtain more complex cable scenes. Chroma keying technique segmented the blue screen background and the green poking tool. Our custom marker detector detected the UV fluorescent markers and tracked them. These marker tracks enabled optical flow computation by interpolating between these marker tracks. Finally, compositing multiple single cable clips onto each other and changing the background gave us more images or video clips of more complex scenes. This is a sample composite clip of the moving cables dataset. You can see the color images at the top left, then the optical flow ground truth, the instance segmentation ground truth, and the bottom row depicts optical flow predicted by several methods we evaluated on our dataset. The methods segment moving cables by first predicting the optical flow and then thresholding it or thresholding its magnitude by a fixed constant threshold. When the optical flow at a certain pixel is larger than this threshold, the pixel is labeled as moving cable. In these figures, it's depicted in red. These are some state-of-the-art optical flow predictors we evaluated first on the dataset. When we chose the mask flow net to improve, and we improved it first by retraining it on traditional optical flow data sets using a different loss function. This gave us MFN probe with improved accuracy on the moving cables test set. Then we utilized the moving cables training set to fine-tune the mask flow net network on a mixture of traditional optical flow data and or the data sets and our moving cables. This improved mask flow net FT means fine-tuned. And finally, we did the same thing with MFN probe, which gave us the best method overall on the moving cables test set. These are some real-world samples where the where we evaluated all these methods, and you can see the moving cable segmentations in green. Our methods currently have the limitations that they assume that there is only a single cable moving in the scene. Last or this week we submitted another paper which addresses the more general case where the grasped cable can perturb neighboring cables and therefore causing multiple moving cables. So that's like a submitted work. Maybe one last thing to note is that this sum plus Dino method, which is segment anything and Dino feature selection, is not very good at segmenting like cluttered cable instances. Thank you for your attention. Well, I think it's kind of doesn't matter how fast they move. It just depends on the speed of the compute. Yeah.
So good morning, everyone. My name is Libor Přeúčil. I'm heading Intelligent Mobile Robotics. So I have 1 minute for just brief intro. So what we are going to present now are two, let's say, reasonable, nice results we achieved last year. One focuses some parts of vision-based navigation solution. The other one, let's say, deals with some kind of optimization or maybe more computational geometry problems. Moreover, we achieved 2 more journal articles, from one of which was in D1. The other one by Scopus is Q2. We had 3 conference articles, 2 Core A, so that was CIIRC, and the other one has not been assigned some grading so far, but it's in the process. At the moment, we have 4 running projects. We participate on RoboProx project. And beside this, what is listed on this slide, we also defended 2 PhD students. So we've got new 2 doctors through the last year, where one of the theses is in the closest selection for Werner von Siemens Prize for Best PhD thesis. So now I'll give floor over to Tomáš, who is going to present the first paper.
Okay. So good morning. Today I would like to present to our paper on model-free ranking for visual place recognition with deep learned local features that was accepted into transactions on intelligent vehicles. We solved visual place recognition task, which is task of searching for the location from which a query image has been captured. Individual locations are usually represented as a database of image, so we are searching for the most similar image from a database, which is similar task to image retrieval. Because compare a query image to all images in a database in some exhaustive manner is not always possible, the recognition is divided usually into filtering and ranking stage. Filtering stage uses some faster method that preselects the best candidates that are compared more in detail in the ranking. And in a ranking is very often used spatial verification of local visual features matched between images. And there are 2 approaches for spatial verification: model-based systems tries to estimate some transformation between images and verifies the consistency of found model. And model-free approaches tries to compute the similarity directly from picture matches. And in our paper, we focus directly on this model-free ranking stage. And the possible applications of visual place recognition in mobile robotics are mainly some basic localization, and also visual place recognition is often used in SLAM system, simultaneous localization and mapping system, for detecting loop closures, which is visiting the same place that then triggers some optimization of a map. Our work was inspired by a previous system developed in our lab by former colleague Luis Gomez Camara. That system used deep learned local features extracted from convolutional neural networks. This system also used recognition divided into two stages. And in the ranking stage, it used a ranking based on concept of anchor points, and this system achieved state-of-the-art performance few years ago, and it evinces high robustness to varying conditions, which is important property for possible applications in long-term autonomy. So we are motivated by this system and focused on the other possibilities for ranking methods. We designed 3 new approaches, and these approaches were integrated into a new system that used in a ranking stage D2net local visual features. And this new system was compared to several state-of-the-art systems. The experiments were performed on 6 public datasets for long-term autonomy. And our main achievement was that one of our methods combined with another system, mixed VPR, used in the filtering stage for repair selection of candidates. This system achieved best overall results from all tested systems. So that's quickly about my research. Thank you. Yes. Yes.
What he does, he usually calculates in his database offline some features, and then he only quickly computes the feature on the query image and compares these signatures. And it seems to me you did it different.
Yes,
so
a little bit.
I understand it correctly.
I think that what Ondřejkum and his group did is computing some global descriptor for the whole image, so they are able to quickly compare the images. So that, as I said about that, there is a filtering stage. Usually these methods are used in the filtering stage, and because computing the local visual features is much computation dependent, this is used only for the ranking for some best set of the images. No, we considered it later, but we didn't try it.
Okay. So hello everyone. My name is Jan Mikula, and I will present a software paper called Trivis. It's a versatile, reliable, and high-performance tool for computing visibility in polygonal environments. So in polygonal environments, we can have multiple types of queries. For example, we want to determine visibility between 2 points, or we have a point and a direction, and we want to compute intersection point with the environment, or we want to know all visible vertices from a given point, compute visibility polygon, which is the whole region visible from the point. We have 3 types of visibility graphs, and sometimes we might be interested to compute all these queries under limited range constraints. So here's an example of efficient algorithm to compute visibility polygon. It's called triangular expansion algorithm, and it operates on triangular mesh. And as you can see, it kind of rotates around, it expands triangles, and as it does so, it computes the polygon. So here comes our contribution. We implemented Trivis, which is a new standalone, versatile, reliable, and high-performance tool. It's a C++ implementation of the triangular expansion algorithm, or the TEA, and it has been adapted to all the visibility queries that I mentioned at the beginning. We did some improvements. So for example, for 2-point visibility and ray shooting, we improved the query time from NH to N, where N is the number of vertices and NH is the number of holes. Then we have efficient limited range queries, which means we expand minimum triangles under limited visibility. We have rapid point location queries due to bucketing technique. We compared our library to CGAL, which is kind of the default option in computational geometry. It's a computational geometry algorithms library. And we found out that we are more robust, that the implementation in CGAL are crashing and they are infinitely looping, and it doesn't happen in our case. And we are also about 10 times faster than CGAL. So here's the example of the improvement where we have directional TEA. So we are only expanding triangles in the direction of the ray, which improves computational efficiency. Here are limited visibility queries, where you can see that yellow are the expanded triangles, and as the visibility is smaller, we expand fewer triangles, which again improve efficiency. We tested our library on a dataset of large polygonal domains, which had around 8,000 vertices and 600-700 of holes, so quite complex environments. And here are the results of runtimes. So we recorded initial time and preprocessing time. Initial time is constructing the environment. Preprocessing is some official preprocessing operations, such as constructing the triangular mesh. And then query time is the average query of computing visibility polygon. And as you can see, when we combine the initialization and preprocessing time, Trivis is much faster than some CGAL variants that we tested. And especially when looking at query times, Trivis takes just about 9 microseconds, whereas the most robust CGAL implementation takes 142 microseconds, so which is at least an order of magnitude of improvement. So to conclude, Trivis is performant, it is reliable, it avoids crashing and infinite loops, and it delivers consistent output, which CGAL sometimes does not. It's versatile, it has user-friendly API for all the queries, and it is independent of external libraries, which means that all dependencies are bundled with the code, and it's freely available for private research and institutional use, and it's on GitHub. And that's all from me, and I'll be happy to answer any questions. Can anyone use it? Yes. Yes, exactly. Sure.
Okay, so let me say something about applied algebra and geometry group in the meantime while they set it up. So we work in computer vision robotics, deal with things which are related to basic research, mathematical understanding of the topics, but also applied things leading to understanding and developing things in computer vision. The group originally included also Josef Šivic, but he has established his own group this last year. So we are currently basically led by me and with Torsten. And this year, actually, we have a very important achievement, which was Torsten's paper, which received a prize at CVPR for the best student paper. So this is a really outstanding achievement, and Torsten will talk about it. So first, you will hear about 2 results from Torsten, and I will add another result from my group. Torsten.
Yep. This is actually work by Sehao Yu, who's currently actually visiting CIIRC. I'm going to present 2 papers. both in the same field. The first one will take slightly more time. The other one's quicker. So we are looking at the problem of 3D reconstruction. So we're given a set of images, and we know where they were taken in the world and the intrinsic calibration. And what we would like to do is build a 3D model of the scene. And traditionally, this is you either reconstruct a point cloud or some triangular mesh. Then you can render it from new perspectives. You can use it for path planning for robots and so on and so on. And about 3 years ago, something called neural radiance fields popped up, where the idea is you don't explicitly represent geometry, but everything is represented implicitly through the weights of a neural network. These are results that I presented last year here at CACORR from some work by Jonas Kohanek, and where you can see that like this implicit representation can give you highly photorealistic renderings or representations of the scene. These radiance fields work as follows. So if we want to render an image and we want to get the color for a pixel, we shoot a ray through that pixel, sample points along the ray, and for each point, we do a lookup in the radiance field. So we apply a neural network, compute a color, and then we aggregate the colors. However, this is highly inefficient. Modern GPUs are not very good at it, which means rendering times, training times are rather slow. Like soon after neural radiance fields, about a year later, something called 3D Gaussian splatting was proposed, where the idea is we represent the scene through hundreds of thousands or millions of 3D Gaussians. So each Gaussian is defined by position, covariance matrix that defines a sphere, and some view-dependent color function. And the nice thing about these is you can render them very efficiently by projecting them into the image, which can be done using traditional rasterization pipelines, which is essentially the thing that GPUs were made for in the first place. So you can do rendering very quickly, can do it real time, even in a browser. So this approach can, again, like build 3D models that are photorealistic. So this is a rendering of a reconstruction, not the actual images. However, the original formulation has a few issues. So this is what happens if you zoom in into the scene or change the focal lengths. And as you can see, structures are much thinner or much thicker than they're supposed to be. And that's not a coincidence. That's by some design choice of the original algorithm. So the idea is we have a 3D Gaussian, 3D object, which we represent by a sphere in 3D, which gets projected into an image and results in a 2D Gaussian. And this Gaussian splatting method tends to generate many small Gaussians in order to be able to represent fine details, which in turn lead to numerical and other issues during optimization. And one thing that the paper does, although it's not mentioning it, is it's using a 2D dilation to ensure that each Gaussian is projected to at least a pixel, so that you don't have Gaussians that don't have contribution to pixels. And that makes training better, but also introduces problems. So here's one example of a dilation artifact that occurs if you're zooming out or moving away from the scene, because something that should be projected to less than a pixel, all of a sudden, due to this dilation that enforces that it projects to a pixel, looks much thicker. So the spikes of the bike should be much smaller, but you get them thicker because you enforce that they project to that they cover at least a pixel. As a side effect, what this can lead to is degenerate Gaussians that are infinitely thin, and that still project a pixel because you enforced it to project to a pixel. Similarly, if you have these very thin Gaussians and you zoom in, you see these very thin structures that are not realistic. So you get these ghosting artifacts here in the background. So the observation is that like small Gaussians, like they are needed, they represent fine high frequency details, but they also these high frequency details cause problems. Luckily, there's a principled way of handling high frequency details, which is to apply some form of low pass filtering. And you can do this both in 3D by enforcing that the Gaussians have a certain minimum size that depends on your training data, and in 2D by simulating like the physical capturing model. Here's a comparison. On the left, you see the original Gaussian splatting formulation, that does not take the size, does not do low pass filtering. On the right, you see our formulation. As you can see, we are able to recover the scene in much more detail. We avoid many of these degenerate effects. And as always, code is publicly available. Do you have any questions? Well, I'm going to talk to you once more, so good. Okay. So the second one is also about 3 Gaussian splatting. The paper is called Wild Gaussians. It's with Jonas Kohalnik, Song Yupeng, Susanna Kukulova, and Mark Polyface, and was presented at CIIRC last year, which is one of the bigger or the biggest machine learning conferences. What we're looking at is, so all of the results that I showed previously were obtained on nice data, in the sense of that images were captured with good cameras. A lot of attention to detail went into the image capture process, and they're all captured under roughly the same lighting conditions. If you want to reconstruct images, say from scenes from, say, images downloaded from the internet, you actually don't have these properties. You have images taken under different conditions. You have images taken with different cameras. You have occluders and whatnot. And we would still like to be able to reconstruct it, and we would also like to take advantage of the fact that we have images under set different conditions, so that we should be able to relight the scene as we wish. So as I mentioned, we go from a setting where we have control over the image capture to one where we don't have control. So we have to deal with images taken under different illumination conditions. We have these occluders, especially in front of landmark buildings, a lot of tourists that get captured. And if we don't model it, we'll get something like this. The colors are a bit blurred. They are not fully consistent. So here in the bottom, you see things that are darker than they are supposed to be. You get these occluder things that come from effects where people were in the picture. So this needs to be handled. And we handle them using 2 effects. The first one is handling these appearance changes. We're not only modeling like the standard Gaussian, but equip each Gaussian with a learnable vector that effectively encodes how the Gaussian would look like under different conditions. And we also compute a learnable vector per training image that essentially encodes what are the conditions in this image. So it's taken at dawn, during the day, at dusk, and so on and so on. And by combining these 2 embeddings and feeding them through a neural network, you can essentially compute a function that takes the original color function of the Gaussian and maps it into something else. It's a fine transformation of the color function. So you get a new set of Gaussians where the positions of covariances are the same, the color function has changed. And that allows you to render the image under different images under different conditions. And this embedding space of the images is rather smooth, so you can actually do meaningful interpolations in these appearance space. So you see 2 target images, and we smoothly interpolate in embedding space and then render the scene with different embeddings. The other thing is handling occlusions. That's mostly a problem during training process. We have images where there are occluders and you don't know a priori where the occluders are. So what it amounts to is that you have an image, training image, where there's a person in it. Your rendering ideally should not have a person in it, and you need to be able to handle this when training the representation. And we do this by extracting a set of pre-trained features, dino features mentioned in one of the previous talks. And based on the dino features extracted in the image and the rendering, we try to get an estimate of which regions in the image are likely occluded, have a high uncertainty, so that if we compute a loss between those 2 images by essentially computing a color similarity per pixel, we take this uncertainty into account and try to not weight pixels with a high uncertainty. And this uncertainty prediction is trained during the reconstruction process. Here are some results on a data set with lots of occlusions. This is a standard Gaussian splatting formulation where you see there's lots of occluders because it doesn't handle them explicitly. And these are our results where you can see that we are successful in removing these occlusions. Here's the same results that I showed before. This is Trevi found in Rome, where we're able to A, remove all occluders, and B, we can render the scene from new viewpoints under different conditions. So we can create these nice fly-throughs. So this works quite well, but it requires that the scene is captured under different conditions. One of the things that we're currently looking into is, can we actually train such a model where we can change appearance without having training data under all conditions? So assume that you only had captured the Davidska campus in summer. Can you actually predict how it would look like in winter or in different night conditions? The first thing that we did was we looked into diffusion models to be able to predict how a scene would look like under different conditions. Not quite working as we hoped it would be, so it's ongoing research. And yeah, if you have any questions, please feel free to ask. I think like handling these predicting appearances, realistic appearances, in a way that generalizes is like more challenging than we thought it would be. And I think you could spend a PhD on this. And I think it would be interesting because if you can do this, you can create quite photorealistic simulators. You could like you would reduce the amount of data capture you would need to build simulators and so on and so on. So I think it would be worthwhile.
Okay, so I will present a result which is a basic research, mathematical, with my colleagues Tim Duff, Kathleen Kohn, Anton Leikin. This has been published last year in International Journal of Computer Vision. This is a top journal with simply one of the best in the field. And the result, the work is about 3D reconstruction. So the problem is to have images, as you see on the panel on the top left, and coming out with a 3D reconstruction, which was shown below. So this is the basic problem of computer vision. There's many applications like 3D reconstruction, which you know from Google Maps and elsewhere, or movie industry, where you want to combine a synthetic world with a real world and produce special effects, and elsewhere. So the problem here is to take a set of images and create a 3D reconstruction of the scene, including 3D points and including camera poses, and have basically a geometric understanding of what has been seen. This is classically solved by kind of a pipeline which first takes images, then using machine learning establishes kind of tentative matches between those images, which are of course not perfect. And in order to arrive at something which makes sense, it uses a small computational, or small, I mean, many computational kind of problems which are based on finding, or which use actually the principle to find the largest consistent subset of those matches, which somehow fits to the geometry of, possible geometry of cameras. And our work is about these problems, how to find which problems are there and how to compute them and how to assess how difficult they are. So this is a basic problem of computer vision, the basic problem of understanding what we can see, what we can reconstruct, and how we can deal with that. So let me say what this minimal problem is, just an example. So you can imagine we are estimating some model from data, and in this particular case, we have a model which is a line, and the data which are just points in space. And this is given us This is determined by solving kind of two linear polynomial equations. It's a very simple problem. And the minimality means that we have exactly as much data to uniquely determine what is necessary. And of course, what is not minimal, for instance, if we don't have enough data, so we would have too many models, infinitely many models, or we have too much data, so that there is no model which would fit them, like 3 points in a plane would not be explainable by a single line. So the problem here is to somehow look at these problems, which are 3D reconstruction problems, and we say they are minimal if the number of solutions to these problems is a finite non-zero number, smaller than infinitely, for a generic, that means in human kind of understanding, random the input data. And in this particular case, we are solving for something like a pose of the camera and pose of those 3D points in the space. And the fundamental research question is, what are these problems? So let's say we have 2 cameras, 3 cameras, 4 cameras, and so on. We have some problem, we have some points in space, some line in space. These points may be incident to those lines. And the question is, what arrangement of points and lines in space and cameras can give us problems which are exactly solvable and can be obtained by this approach? So there was a result which we published in 2019, which found that if you see all these points and lines in all cameras, and if you use all the knowledge which is there, so there are exactly certain minimal problems, and not more and not less. And this result received that time the student prize at CVPR, at ICCV, which is something similar to what Torsten received this last year. Now, the new result, which actually I should present now, is going beyond that. The question is now, what if we don't see everything in every image? So what if we don't detect some point in some image or some line in some image? What if we miss something? And for instance, this is the case, right? So we have 3 images and there are 4 points in space. There is 1 line in space, but in one image, we don't see 1 point which is on a line. In the middle image, we see everything. On the right image, we don't see the line, or we don't detect the line. So this is very realistic scenario, which happens very often, but the scenario is much, much more complicated than before. Before, we could show that if there are too many observations, then we can't really find any model which would explain them. And now we are in much more difficult situation when there is infinitely many such problems, because you can always add some more views and remove some points, and you can balance already like how much you see and how much you want to compute. So this opens a large space of problems. So we started with something which is simple as possible, but already something more than before, and we assumed only to have 3 views. Still, this is very hard. Still infinitely many minimal problems. And in order to be able to deal with that, we somehow added some technical condition that these lines can be somehow adjacent to like maximally 1 point. So this was technical condition. So it doesn't get all things in 3 views, but it gets many, many things in 3 views. Still, it's hard. The result here, which we got, is that we completely classify all minimal problems for these 3 calibrated views with that technical condition, and we found that there is 74,575 classes of the problems. Each class is infinite, but these classes can be described. And not only can be described, we can also somehow assess the difficulty of each of the class, which is basically related to the number of solutions which each problem in the class has. And this is some kind of a table which shows that some of the problems are simple. There are many of simple answers, relatively simple. Some of these problems are very hard. There will be thousands, tens of thousands solutions. So these problems are hard and are not really practical. But these guys which are here are practical. So we can classify things which don't have any incidences. So these panel shows kind of a pictures, like the top left says, well, there are 3 images. Each image sees 3 points and 1 line, and so on and so on. So these guys are problems which don't involve any points sitting on lines, for instance. And you may see the numbers below these tiles. They show basically how difficult the problem is. So if something has a number 80, it's relatively easy. If something has number 1456, that's much more difficult. Okay, so the point is this. So we explained many problems in geometry of 3 views, which really actually extended a long list of research or trifocal geometry, which was here, like 100+ papers which appeared in past. So we basically gave much, much more before. Humanity knew something like 66 problems of this type before, and now we have 74,000 problems. So we know much more now than we knew before. Thank you. So, okay, there's some kind of two components. You prove something by using combinatorics, methods for algebraic geometry, and then you set up a computational problems which will try to enumerate certain things, and you go through that. It's basically kind of combinatorics plus verification based on some theorems. So it's a partly theoretical in terms of using human brain to come up with some result, and partly computational, where you have some set of candidates, which is potentially very huge, and you want to basically verify which one of those things has satisfied certain conditions. So basically that's it. Yeah, each class represents some kind of particular problem, like 3 points and 1 line, and now in one image you see everything, in one image you miss something, in the other image you miss something. Yeah, you have to set up you prove certain things which basically limit you to certain number of cases which are possible, and there are some other conditions which can be checked, like per case you check, okay, is the Jacobian of this thing full rank or something like that. That can be computed in some sense by a computer. And there's of course some important principles that in this world certain things can be proven by having a nice example. So if you find a nice example and you show it on an example, then you know that this will hold for all generic examples or all generic cases. It's a very strong thing which holds in algebraic geometry.
Thank you very much. Let's
Okay, so thank you very much. I'll present some of the results of the intelligent machine perception group. We've selected 3 publications out from the list of all the publications. I would like to also mention, I think, other kind of notable thing. We have 3 PhD students. One of them defended already in December, and 2 have submitted the thesis. So the 3 results are here. I will start with the first one. So we do research in computer vision robotics and more recently in machine learning for life sciences. So we'll have in each of these 3 domains. I will start with the first result. This is a result of Tomáš Souček, who has just submitted a thesis, already started a job at Meta in Paris. This work was published at the IEEE transaction of pattern analysis machine intelligence, which is one of the top journals in computer vision. The problem we are looking at here is if you are typically, if you want to set up a robot to do something, you usually have to manually define what the success is. Whereas ideally, we like to have the robots to really be able to learn from, say, videos, how the world, how the actions on the world are changing the objects. So here we are looking at this problem, but more from the learning side, from the computer vision perspective, where we are looking at how, trying to learn how people, when they interact with the world, how they are changing what we call states of the objects, like having an apple, which is, whole or then being cut. So we've developed, the problem setup is that we have a large collection of instructional videos where people are interacting with the world and changing the objects, achieving certain tasks. And our objective is to learn a set of classifiers which will understand in what state the object is. And also ideally the action which is changing the state of the object, like cutting by knife is changing the state of the apple. And we like to learn this automatically without any annotations. So that's the objective, because the annotation is expensive. The problem is difficult because we have there's a large variability of the visual world. Videos are long. You can imagine someone showing for 10 minutes how to do something, and there is a lot of noise. Our key contribution, we designed a self-supervised learning algorithm, which can learn this automatically by incorporating several constraints on this problem. I will not talk in detail about this, and we've investigated different architectures for this problem. Here are, I think, the 4 examples. The spoiler is, this one is the best, but we have sort of computational results for this. We've applied this on several public data sets on which we evaluated how the technique works. It works significantly better than what is currently available. The results are not just a couple %. The difference is quite large. And now we are looking into applying these models on the real robotic setup, but this is ongoing work. So the second work, which we would like to show, will be shown by Katerina Zorena. This is more in robotics. This is work which has been published at the RAL journal. We like to publish there because of a very quick turnaround in the publications, and it's a good review process. Katerina, please.
Can I switch the slide? Okay. Okay, so my name is Katerina, and today I will present, there is my picture. I will present a temporal consistency for object pose estimation from images. The main motivation for this work comes from robotics. So on the next slide. Thank you. You can see the example of Atlas robot from Boston Dynamics manipulating the object and putting this, probably a car part, to some designated place. And stable and temporal consistent object pose estimation is really important for object to not have some additional unexpected motion. And another motivation is handover from human to robot. So here it's also very important that the prediction of the object that robot wants to grasp is really consistent, because, for example, if the object is suddenly 20 centimeters away and robot would reach for it, it can potentially harm the human. And those are not empty words, because the other day in the lab, I was doing some experiment, and when the object is fully occluded by a piece of paper, the robot really moves suddenly. And if not quick reaction of my colleague, would have been painful. So the problem formulation for our work, no, actually not yet, the main goal of our work, no, the next slide, but I just started talking a bit, yeah, anyways. The main goal of our work is to create the temporally consistent object pose estimator. And here are some more examples. You can see the estimation of off-the-shelf algorithm cozy pose on 3 frames that come from camera attached to the robot hand. And on the left image, okay, so the cozy pose estimation is shown in red contour. So this is the object pose. And on the left image, where an object is clearly visible, the estimation is fairly good. But as soon as we have partial occlusion of the object, the contour is off, and also the rotation, for example, in the right frame is really off. And if we plot this in time, we plot the next slide, the rotational component in time. This is a 1D representation of rotation. It's really stable while we see the object, but as soon as it's occluded or some other something else wrong happens, there is a lot of noise. And our goal is to reduce this noise and have a more consistent estimate. Next slide. Thank you. And have a more consistent estimate for better control of the robot. Next slide. The problem setup is that we have the robot with camera fixed on the robot hand. And next slide. We want to perceive the object pose or the transformation from the camera frame, that is a blue and green arrow here, to the object frame, which is red and green arrow. And we do this in time. So we'll receive a stream of frames from the video, and the robot can move and the object can move. But since we know that camera is rigidly fixed on the robot, we know the pose of the camera. And the task is to find the pose of the object that would be consistent over time. And our approach to this is to build, to combine probabilistic models and motion models. So for motion models is that we make some assumption about the object. So how much the object can move. And for example, if it moves with certain velocity, it will continue to move with the same velocity in the next frame. And also we represent the uncertainty of our current object pose estimate. So for example, in the very first frame, when we just have the prediction from off-the-shelf 6D pose estimator, we know that it can be quite not accurate in the depth dimension, because the difference between the object when it's closer or further from the camera is not that big as when it moves to the side. So here you can see that the uncertainty in the depth, so from pointing along the ray, pointing from camera to the object center, is higher. And also if we don't see the object, our uncertainty about its pose will grow over time. And And in our method, we will discard everything where the uncertainty of the current estimate is too high. We'll just discard those predictions. So next to some examples. In the first example, you can look on the mustard, and when it's partially occluded by the box, the cosipose, so the red contour prediction, is high and less accurate, while we maintain more stable prediction. And the next example is the task when robot is tasked with tracking the object. So the robot hand will follow the object when the object disappears behind the paper, so the full occlusion. Cosipose method cannot predict where it is, but since we have this assumption that object stays the same or moves with the same velocity, we can still predict its pose and have this more stable control. That's it from me. Thank you.
So thank you very much. So Katarina is a PhD student in our group, and she's finishing writing up her thesis, so which is going to be happening soon. And the last talk, which is going to be given by Roman Bushuev, who is also a PhD student in my team, but jointly with the team of Tomáš Pruskal at IOCB Prague, which is just across the street. It's of organic chemistry and biochemistry. And he's going to talk about actually combo of two papers, one at NeurIPS, which is one of the top machine learning conference, and the other one which just got accepted to Nature Biotechnology Journal, which is one of the top journals in biology with a very high impact factors for us. It's like one of the first achievements in this area of this caliber, so we are very happy about this. And Roman will tell you more about this very interesting problem he's looking at. Roman.
Hello, everyone. My name is Roman, and I'm going to, as Joseph said, I'm going to present briefly two papers, and both of them are on machine learning for the discovery of new molecules from nature. So the nature is truly incredible. Living organisms act as real chemical factories, producing a diversity of molecules, and each molecule has a unique structure and function. So here you can see some examples. So this molecule on the top left is the luciferin, which is characteristic for this emission of light in fireflies, for example. This cinnamaldehyde, this small molecule in the bottom left corner, is responsible for this very nice smell of cinnamon. Or this lycopene long molecule actually colors tomatoes red. Or as you may know, this very well-known antibiotic penicillin actually comes from fungi. So obviously there are many, many more molecules in the nature, but the question is how many of them do we actually know? So unfortunately, it turns out that we still don't know most of them. Even in a simple organism such as E. coli bacteria, we have not yet discovered more than 80% of molecules. So in more complex organisms such as plants or a human body, these numbers are even higher. So now the question is, how can we even discover new molecules? Well, the most prominent technique is mass spectrometry, and the workflow can be summarized roughly as follows. So first, a biological or environmental sample is prepared, for example, by grinding or mixing it with something. In the second step, it is analyzed in a mass spectrometry system, which, roughly speaking, measures masses of individual molecules and also masses of their fragments, enabling to kind of produce a unique fingerprint for each molecule, known as its mass spectrum or tandem mass spectrum or MSMS in short. And then the ultimate goal of mass spectrometry is then to decode these fingerprints into complete molecular structures, allowing for the discovery of new molecules. But unfortunately, in this pipeline, it's a main bottleneck to decode molecular structures from mass spectra, and even, let's say, state-of-the-art machine learning models are still not able yet to annotate more than 90% of mass spectra with molecular structures. And this is exactly where our work comes in place. But instead of directly predicting molecules from mass spectra, our approach is based on two steps. So in the first step, we kind of train a machine learning model to first understand the mass spectra, or let's say to make sense of them, or in other words, to predict some meaningful representations of mass spectra. So in such a way that they encode some properties of molecular structures. And let me just briefly introduce what these representations are. So similarly to how ChatGPT is trained to understand text mainly by predicting masking parts of sentences, We also train a neural network called DREAMS, which is trained to understand mass spectra and the underlying molecular structures, mainly by also predicting masked parts of mass spectra, some signals in this mass spectra. And as a training data, instead of the whole internet, which let's say was used to train ChatGPT, we use something very similar to the internet, but in this world of mass spectrometry, which is a huge repository of mass spectrometry-based experiments deposited from different biological or environmental studies. For example, some clinical studies of blood or some beer analysis or some, let's say, plant extracts and so on. So in total, these repositories comprise like thousands of such scientific experiments and with millions of mass spectra in them. So indeed, once we train this ChatGPT-like model to unmask hidden signals in mass spectra on these millions of training examples, we observe that it derives some representations of mass spectra that capture molecular structures exactly as we wanted. And this is shown on the right. So each point here is this representation of a mass spectrum, and colors denote some molecular properties. And we can clearly see that even though the model was never trained on molecules, only on mass spectra, it can separate, for example, carbohydrate molecules shown in green from the molecules with more exotic chemical elements shown in pink. So and why is this representation so interesting for us? Well, because having them, we can kind of start navigating this whole internet of mass spectrometry data. So what is shown here, each node is again a representation of a mass spectrum, and the edges somehow connect them so that it tries to cluster similar molecules together. And in this particular example, we can see that we can kind of form a hypothesis that psoriasis disease can be somehow provoked by a fungal pesticide. And to the best of our knowledge, this hypothesis hasn't been established before. But this is just one particular example in this huge internet of mass spectrometry data. If we look at other examples, we can find potentially new cancer biomarkers. In other words, molecules that can help identify cancer. We can also find some interesting plant-specific metabolites, which seem to be abundant across different plant species. So further in the same work, we also show that these representations can not only help to, let's say, connect different studies or molecules together, but also to predict some properties of molecules. So not yet complete molecular structures, but some interesting properties such as drug likeliness, for example, or some molecular complexity, which is interesting because it's a potential measure to search for new life beyond Earth when mass spectrometry is implemented on the space stations. So regarding the next step, obviously, we are not the only group in the world working on this problem. Actually, there are many people in the world having the same goal to decode molecules from mass spectra. But unfortunately, currently, it's really challenging to compare different methods across different groups in the world and actually to measure progress in the field. So therefore, we first decided not to develop a model, but first to establish a community-wide benchmark so that whole community agrees how we should validate the models and kind of proceeds further together. And I will just briefly introduce the main components of this benchmark. First, it contains the largest public data set of mass spectra labeled with molecular structures. And actually, the big part of this data set was measured in our group at IUCB Prague. The second component is a new non-leak and train test data spread. What it means is that if we see that some method performs really well on our benchmark, we really want to make sure that it's not because it, let's say, memorized the training dataset, but because it really generalizes to the discovery of new molecules. And the last part is predefined tasks and evaluation metrics, meaning that the whole evaluation protocol is consistent and easily reproducible between studies. Also, we provide an online leaderboard allowing for continually measuring the progress in the field and also reporting the performance of new methods. Yeah, and finally, our current and future work, let's say for the next year, is actually to developing a model that can decode complete molecular structures based on our DREAMS neural network proposed in the previous work, which I had just introduced. Yeah, so that's all from me. Thank you for your attention. So it's based on some structural similarity between molecules because we want to make sure that model predicts really new structures So in the test set, we have some structures which are completely different based on structural similarity. It's something like edit distance on graphs of molecules.
And I will just add, it's a very important question. It seems in all the several biology problems, the data leakage, it's sort of one of the key questions we can discuss later, but it's very important.
Thank you. The group is Department of Industrial Informatics, which is a group headed by myself. So I will briefly say about our publications that have been either accepted or that have been published in 2024. So we can see here two publications in International Journal of Operations Research, which is a very highly cited journal, and then the best results has achieved Mohammed, who is co-author of several of those papers. But we see also publications in multiple transactions on intelligent transportation systems, in computers and operation research and so on, typically solving scheduling and combinatorial optimization problems. A part of that, from the team of Lukáš Krpa, we have three nice papers in CORE A-star conferences, ICAPS and ICIIRC. So that's about publications. We typically have quite broad collaboration with industry, which was also continuing in 2024. Unfortunately, the budgets are, especially of automotive companies, are shrinking. So we probably in future will have less financial income from that, but I hope that we will still keep like expert collaboration with them. It was about autonomous driving, about simulation of some external components in automotive, and also about energy efficient energy production, robotic production, sorry. As far for today, we have 4 talks. As probably you might know, I'm principal investigator of the RoboProx project, and as such, I have a lot of duties related to management and administration of that project. So I'm happy to announce that Přemysl Šucha, who is the first speaker, will be head of the department starting from the 1st of February. But don't be sad, I am still here, so you can meet me and invite me for lunch if you want. Okay, so Przemek, please come here, and the floor is yours.
Good morning. I will present today joint work with Pavlína Koutecká, who is our former master student, Jan Hula, and Bruce Manhood from Ghent University. And I will talk about improvement of this method using machine learning. First of all, I will just quickly introduce what the branch and price is, because that's in combinatorial optimization, very famous method, and it's a state-of-the-art method for many combinatorial problems so far. The method is based on so-called Danzig-Wolf decomposition, which, unlike like traditional approaches where you like look at the problem from the global perspective, you make all the decisions at once. Decomposition focuses on like specific sub-problems that we can identify in the combinatorial problem. A typical example is the vehicle routing problem, which is the problem you might know from classes of combinatorial optimization. It's a problem where you have a fleet of vehicles, set of places defined by a graph, and you need to cover those places by routes. So mean like it's like good distribution those are this type of application. This is a classical example where you can apply branch and price and dancing pool decomposition. So the idea is that instead of making like particle decisions, we construct individual routes, like it is illustrated in the figure on the top right. So here is a trivial example with 3 routes, 0, 1, 0, 2, and 0, 3, and that corresponds to the appropriate master problem, having 3 decision variables, saying whether we will use that route or not. Of course, this is not enough. We might have like much more routes, and therefore the routes are generated at runtime. So we add them one after another because we cannot assume all of them at once because there would be exponential number of them, and therefore we have so-called subproblem that continuously generate new routes. The branch and price is like relatively complex approach, but I will just briefly introduce the main components because it's important to explain our idea. The core part of the branch and price is column generation, which solves the linear relaxation of the problem. And the integrality of solution is handled by so-called branching, which is in fact just the branch and bound approach. And altogether, this is called branch and price. Column generation, as I already mentioned, has 2 parts. It's the master problem that combines the routes in case of the vehicle routing problem, and one or multiple subproblems that solves like the decomposed problems, some particle subproblems of the whole problem. Another purpose of the subproblem is to detect whether we can stop the generation of new columns, or sometimes called new patterns, the routes. It is based on the reduced cost. If none of the subproblem is able to find a solution with the negative reduced cost, then we can stop the column generation. And actually, the good property of this algorithm is that like there are many places where we can apply some improvement, and also the improvement can be based on machine learning. The idea of like applying machine learning to the branch and price is not new. Nevertheless, the first paper in this direction was ours. It's Václavík. Another co-author is Tonda Novák, me, and Zdeněk Hanzálek. It was the first paper that tried to successfully applied machine learning to speed up the branch and price algorithm. Apart from that, you see that there are like many other papers. Mostly they concentrate on speeding up the subproblem, but often issue, it is highlighted in the table, they often don't guarantee the optimality of the overall approach, and none of them concentrate on how to manage execution of individual subproblems. And this is the weakness, and that's what we addressed in our paper. Hopefully, our idea is like very simple. It can be illustrated just using those 2 figures. So we run the standard branch and price algorithm on some smaller instances, and we monitor interaction between the master problem and subproblems. So detect dual solutions, we detect reduced costs obtained by the subproblems, and we record that. Then we train a ranker, meaning a machine learning-based model, which is able to rank the subproblems regarding the reduced cost. So we get like estimate which subproblem should be like has a higher chance to achieve solution that can add a new column, new pattern into the master problem, and we solve them according in this order. So if we get one successful solution, then the good news is that we can ignore other subproblems and thus save some time. And that's our idea. We apply this idea to operating room planning and scheduling problem. It's a problem given by a set of patients on a waiting list. So we talk about elective patients, set of operating rooms, and a set of blocks defining availability of surgeons. And the objective is to assign patients to blocks such that we minimize some objective, which minimizes waiting time of patients, number of non-planned surgeries, operation room overtime, and underutilization. Here, the decomposition is based on the block, so it means that we assign and schedule operations in individual block via subproblems. And we apply our idea and tried different models for the ranking. So we assume like 3 possible model types: burst-wise, list-wise, and point-wise. And the best one was lambda-mart with precision 0.92. We implemented this idea into the branch and price approach, and we managed to reduce up to 41% of subproblems. So we were able to skip them compared to the standard approach, and it resulted into saving about 10% of the CPU time. Next slide, please. So to conclude, we developed like completely new method to speed up the branch and price. It exploits the advantage of this decomposition algorithm, and we have like very efficient way to generate the training data, because from single instance we are able to derive like more training samples we can use to train the ranker. And the algorithm was applied to a practical planning and scheduling problem. And currently we are preparing a project with Motol University Hospital about surgery planning and scheduling. Result was published in European Journal of Operations Research. This is a Q1 journal, and we continue with those ideas together with a team of Mikuláš Janota, and we investigate like other opportunities in this domain further. Thank you very much for your attention. We derive features defining the problem instance, and we also observe properties of the master problem, like how many branching decisions we did, what type of them, something we derive from the dual solution, which is a key parameterization for subproblems.
Hello, my name is Mohammed. Today is my pleasure to talk about one of our current research regarding optimal trading strategy in electricity market for the charging station company, which serve both electrical and hydrogen vehicle. Next one. Let's me start with this question. What is the bidding curve in electricity market? Actually, the bidding curve is a pair including the quantity of electricity and electricity price, which both generator and consumer in the market are willing to trade the electricity at those specific pair. In our study, we investigated how to optimize the bidding curve for the charging station as one of most important consumer in the market to maximize their profit. Generally, the bidding curve collect into different key markets, one day-ahead market and intraday market. Probably you know better than me what are this market. But in brief, day-ahead market is a forward market and generally open and close one day before in advance. And intraday market is another market come after day-ahead market and is much more closer to its delivery time as a response to real-time change in day-ahead market. For example, change the weather may affect the generation of renewable energy. So day-ahead market must cover this fluctuation and imbalance in real time in day-ahead market. But one most important point in this two market is frequency of the market update. I mean market time unit. And generally, the day-ahead market updates every hour, 24 times per day. But in intraday market, we have a different time unit, every 60 times, 30 times, and even 15 minutes for updating the market. Many of countries, especially European country, are going toward 15 minutes time unit for updating the price in intraday market. As you can see, in single intraday coupling market, in July 2024, some of countries, I mean the green one, including the Czech Republic, adopted 15 minutes time frame for trading intraday market, and it's planned to March 2025. Some other country add to this market. I'm not sure how much this plan is on track or not, but it shows generally the trend going toward a smaller and a smaller time frame for trading the electricity. That's the reason we also consider 15 minutes time frame unit for our intraday market. It means that we need to optimize 96 bidding curve during the intraday market plus 24 bidding curve for day ahead market. That is indicate complexity of our model, and it should be considered. The bidding curve is not only decision variable in our model, and we have some other decision variable, including operational decision variable for charging a station, how much we should buy the electricity from the grid, how much should be charged or discharged in battery or hydrogen tanks, and so on. And also we need to consider if the electricity price is subject to uncertainty, its complexity will intensify much more. Just suppose we have 3 stochastic scenarios for each quarter. Going forward and through 96 quarter, I cannot imagine how big will be our scenario 3. Even using some scenario reduction techniques, we are facing a problem with 1,000 or even million of scenario. And solving such a complex problem is not possible by traditional computational optimization algorithm or even commercial software. And we developed a decomposition approach, next slide, for solving this problem. We decompose our problem to the master problem and sub-problem first. The master problem is responsible for solving day-ahead market, and sub-problem is responsible for solving intraday market. And then we exchange the information, between the master problem and sub-problem, including we develop one strong optimality code. And also there are a lot of technical details that I invite you to check the original paper if you are interested But still using this decomposition or sub-problem is not computationally feasible to solve. So the source of complexity is 2 things. One, number of quarter, 96 quarter in the sub-problem is very big number. And second, number of stochastic scenario price. Okay, so we follow 2 different approach. First, we develop the second layer of the decomposition. In this second layer, we decompose all sub-problem, but this time horizontally decomposition, and using the forward pass and backward pass for solving our sub-problem. And in the forward pass, we start from the first sub-problem to the last sub-problem, and the backward pass, we start from the last sub-problem to the first sub-problem. And in forward pass, after solving each sub-problem, we transfer the transition variable, including the battery level and hydrogen tank level to the next sub-problem. And in the backward pass, we transfer the optimality code generated to the previous sub-problem, and we repeat entire process until our sub-problem is solved. But even this decomposition, horizontal decomposition, solving the sub-problem for thousands of stochastic scenarios is still impossible. So we adopt a kind of sampling optimization. I mean, instead of solving the subproblem once for all scenario, thousands of scenario, we solve multiple, next slide, we solve multiple subproblem for a small set of scenario. For example, each set including 10 or 20 scenario. And for that reason, we have to develop some special lower bound and upper bound for solving the stochastical upper bound and lower bound for solving the problem. And we develop one specific termination condition for our subproblem. For example, if our stochastical upper bound fall within this domain or subproblem terminate and stop, and then we exchange information with master problem and solve the problem, ensuring to reach convergence for entire model. And in the last slide, I would like to present numerical result provided by our algorithm for solving the problem in a specific setup. And in comparison with some other commercial software, even classical Bender's decomposition algorithm, as you can see in the table, the CIIRC, Groovy, and classical Benders were not able to solve the problem, and generally they face with out-of-memory error for solving the problem. But our proposed algorithm were able to solve the problem in 4-hour time unit after 132 iteration with very close optimality gap, about 2.5% optimality gap. And in our convergence chart, you can see a stability of our algorithm with very smooth trend of convergence between upper bound and lower bound, and also effectiveness of our algorithm for solve and provide high quality solution in reasonable time. That was all my presentation, and thank you.
Please go on.
Does this work? Yeah. So hi, my name is Jakub Metz, and today I will be talking about non-deterministic action reversibility. This work has been done in collaboration with the University of Klagenfurt. Next slide, please. So action reversibility studies whether the effects of actions can be undone by other actions in the domain. It has been empirically proven that action reversibility is present in many deterministic domains that are researched in the literature, and it has application in robotics, system verification, for the guidance of search algorithms, and in other domains where reversibility naturally occurs. Next slide. Thank you. So before we will speak about action reversibility, we will need to learn about fully observable non-deterministic planning, in short FOND. So I will briefly summarize that. So we are given some variables that has finite domains that can contain some values that describe the states. Then we have actions that allows us to change the states of the environment from some state to another. And we are usually given an initial state and a goal state. And the goal is to find a policy that takes us from the initial state to the goal state. So we want to solve the problem that's described by the system. Next slide, please. On this slide, you can see an example of omelette domain. In this domain, we want to make an omelette for us. So we start in a state 1 where we have a pan with no egg on it, and we want to get to state 7 that's on the right bottom part of the scheme. And we can reach that state by applying 2 actions break in sequence, right? But this gets us to the state only if we are lucky, only if we go from 1 to 3 and from 3 to 7. This is caused by the fact that the actions are non-deterministic. So action break can fail. We can try to open the egg, but it can fail, and the egg can fall into pan with a shell. So we don't want that. That's denoted by state 2. And in this case, we want to discard that again and move back to clear pan, clear it, and start again. Or we can try to crack the egg, but it doesn't open. It's just cracked, and we need to open manually once again. That's denoted by state 4. So we have these 3 actions that that takes us from one state to another. And yeah, we want to change the environment from some point to another. Next slide, please. So the contribution of our work was that we've defined weak and strong reversibility. That's inspired by 2 notions that are presented in fund planning. One is weak policy. That's policy that has a chance taking us where we want to. It is not guaranteed whether we will get there or not. Next slide, please. And the second one is strong policy. This is a policy that is guaranteed to succeed no matter what happens. Therefore, we called action weakly as reversible if and only if from each state into which that action can result from some state S, we can return back, or strong if there is a guarantee that we will be able to return back. Next slide. We further focused on 2 specific classes of action reversibility. One is universally reversible. That is, if that action is reversible everywhere, we call it universal. And the second is uniform reversibility. That is, okay, so this action is reversible in that states S, but it can each state can have its own policy, and we don't want that, right? We want to have one common policy that works everywhere in all states, in all that states of the set S. So this is called uniformity, if there is only one common policy for it. On this example, you can see weak reverse policy for states 4 and 5 for action open. As you can see in these red states, you can apply that action. If you apply it in 5, you end in state 6, and if you apply it in state 4, you end in states either in state 3 or in state 2. And as you can see from all these 3 states, 2, 3, and 6, if you follow the proper green lines, you are able to come back to the state from which you left by applying that action. So you say this action is weakly reversible because you have a chance to return it back. Right? On this slide, you see strong policy that works only for state 5. If you apply action discard that we want to reverse now in state 5, you end in state 1. And as you can see, if you follow green lights and you consider all possible changes, all possible effects, you will eventually get to the state 5, and you can't end up anywhere else. So this action is actually this action is strongly reversible in state 5. So our work focused on universal and uniform reversibility. We have several theoretical results. One is necessary condition for strong universal reversibility. Then we have proposed, like the major result of the work is that we have proposed reformulations for weak and strong reversibility to classical and fund planning. That means that we don't need it to provide algorithms for specific algorithms for solving action reversibility, and we could reuse existing planners that work with classical or fund planning. Next slide, please. Next slide, once again. Yeah, and we also have some experimental results. So we have investigated the reversibility of actions among the domains that are used in a community in the literature, and we have found out that we are able to prove some form of reversibility for approximately 68% of actions, where 1/3 of them was identified as universally irreversible, meaning that you can't undo that changes, and 1/3 as weakly universally uniformly reversible, meaning you have a chance to reverse it anywhere by the same policy. And the most important result is that 91% of these actions was proven as strongly uniformly universally reversible. That means 1/3 of actions can be reverted anywhere by the same policy, no matter what non-deterministic effects occur. So as you can imagine a robot, and if you have strongly universally uniformly reversible action, you know that you can do that and you are safe because you will be always able to come back no matter what happens. Next slide. So in conclusion, we have defined weak and strong reversibility for non-deterministic actions in fund planning. We have specifically focused on strong and weak universal uniform reversibility, for which we derive several theoretical theorems. We have proposed reformulations to already existing widely studied formalisms. And we were able to identify that in total 56% of actions were reversible or irreversible. Thank you for your attention.
Okay. A question? So let me ask, so how large are these states that we are exploring, right?
Like that example that we had on the slides, it was like toy example. Usually these state spaces, they are easily bigger than the number of atoms in the universe. So the font domain provides you a compact representation of the state space. So the problem here is you want to essentially find a cycles in that graph, but you need to do it on that abstracted level. You don't have the explicit graph because it would be too big. Yeah, we have a paper from 2021, I think, that's related to reversibility, where, for example, we used it to prove that nature that's present in that environment that plays against agent can eventually be undone, so that if, for example, if I want to go shopping and it rains, I can wait before it stops because it's reversible, right? Because the roads will dry out, and so you can examine reversibility even in this like real world scenarios. But yeah, it lacks applicability for this part.
Thank you. The next talk will be given by Peter. Please go ahead.
Hi everyone, my name is Petr Stejskal. Today I will talk about the control algorithm for new hybrid power plant. We work on this topic together with Ondřej Mamula, Přemysl Šucha, David Hrycej, and Jitka Stoklasová. Please, next slide. I would like to talk firstly about background of the project. Maybe you heard about the power plant in the media. We work on this project for a few years. And also I'd like to highlight that this project is cooperated with Department of Professor Mařík, concretely Group of Energy, presented by Ondřej Mamula. And we are happy that last year we delivered a control system in the power plant, which is in operation since July 2024. Also, during this project, we cooperated with some important partners, namely Siemens, where we work together with on integration into their SICAM environment. Also, we cooperated with Centrax, which is a manufacturer of gas turbines, which are used in this solution. And we work together about detailed modeling of their gas turbines. And also, I would like to name DECI, which is a Czech company and is a final operator of this power plant. And more about this project and power plant itself, it will be presented later by Ondřej Mamula in presentation scheduled later. Next slide. Firstly, before the talk about control algorithm, I would like to say a few words about ancillary services. It needs to be in balance production and consumption in the grid. And this is task for transmission operator in Czech Republic. It's company ČEPS. And this company has opportunity to use some capacity reserve in the grid, which called ancillary services. There are many types, and we would like to focus only for one type, which is a FRR service. On the left side, you can see the figure about how this service could be activated. The red one are positive, so this means that there is added more generation into the grid, and gray one it's that there is less generation activation. On the right side, there is example of how this activation can be looks like. that the red line is that there is some demand, which is control signal from the grid operator, and the provider, the power plant, is react on this signal like blue line. So please next slide. And I would like to talk about the problem statement. For the meet requirements of Asphero services, we have available 6 gas turbines, and also there is a battery system which is able to of quick reaction, but it has limited capacity. In contrary, the arithmetic gas turbines has opportunity to run for a long time, but there are more complicated devices. So there is 16 stays. There is relatively short startup sequence, about 2 minutes, but there is too long deactivation sequence, about 10 minutes. But with cooperation with Centrax, we are able to found some improvements about reactivation sequences. So in some states, we are able to start more quickly. About the problem of control, we are facing to uncertainty of Asphero service because this service can be activated for a limited time. So we don't know how long activation will be, and also there is no guarantee how amount of energy will be activated, so it can change every second in whole range which is cell. And so task for the control is to react to these demands, and what needs to do control must solve is something like a real-time unit commitment. And also as a secondary task, there is optimization objective. So we are trying to minimize operation cost of gas consumption and electricity. And in our solution, we applied techniques of robot optimization. And also would like to highlight that in this domain is very hard to decide when the turbine should be start, stop, or restart. About control algorithm design, I would like to mention 4 main components. We have here a scheduler, which is component which trying to planning in which time one of the turbine should be available in a state we called power state, where the turbine is capable to provide power, and also scheduling times when this turbine should exit this state. Then we have next component, which we call the manager. This component solving the cheapest combination to achieve this scheduled times. It can be defined as a main cost flow problem. And also there is economic dispatcher, which managing the output power of turbines in power state. And as last component, there is a battery balancer, which compensating rest of the needed power, which are not delivered by turbines. Also, I'd like to highlight in this solution digital twin technology. In this project, to solve this this control, we developed twins of turbines. It's based on a complex state model and fully parameterized. And also we modeled battery system, which most were more easier, but also parameterized. And these digital twins help us to create a simulation environment of this power plant. And we were able to test our control against different various of scenarios. And we should, or we could see the outputs of the result of that scenario. To imagine that on the top right corner, there is some graph as output how the power plant will be work. Thanks to this good basement, we could go into a very clever architecture. We could design our control algorithm that the control algorithm can work with power plant interface, that it receives data from power plant and sending commands to it. But we adopt the same interface, and we were able to set our digital twins behind the same the same interface without changes in control algorithm. So control algorithm has no is not able to detect if he controlling against the real facility or our digital twin on PC environment. To conclude this, this is a unique power plant, so thus the unique control is needed to design. In our develop, we focused on effectivity of the solution with respect of robustness coming from a further service. And also we are happy that we not detected any crash of our solution and it's fully reliable. And also we are happy that we achieved a very successful solution come into the industrial environment.
Any question?
The response time of battery system is very quick, at most 2 seconds at full range of power, at maximum by our test. I think that 1 or 2 seconds is okay. Yeah, it can be. Okay, so I should respond. No?
Okay. So that's the plan, right?
And this is your facility.
Okay, so there is subsequent talk by Ondřej Mamola. He will speak more about the facility. Okay, thank you very much. So there is a coffee break, so you have to go through this door to the room beside. We will restart at 11:10, right? 10 past 11, we will continue, right? Určitě, já ti udělám kohostem, jo? Já to si dělám velké všechno.
Jinak teda já jsem udělal jeden slide, tak koukám, že jsem jediný, kdo udělal jeden slide, včetně tebe, který jsem měl 3 slidy.
Někdo neudělal žádný a ten úvod, jako by,
Tam v jeho instrukcích bylo, vedoucí bude mít právě jeden slide.
A já mám 3.
A on má 3.
Chápu.
A kdo to instrukce?
Já.
To je nějaká
Já.
síla.
Ale já jsem myslel všechny ostatní než mě.
To nás chci zeptat dalším tomu.
No, hned to bude, ne, něco dodělám s ním, no. Takže prosím tě, ty jsi...
Já
jsem potřeboval Zoomlink, teďka ten mi tady nechce otevřít. To bude. Já se vám budu nezlobit, já tady musím najít. Takže tebe tady najdu jako Urban, jo?
Já jsem nevěděl, jestli tam jsem
Ty ještě nejseš, tak teďka budu nejdřív vás, no, takže?
V té další sekci, kterou začínám já,
Ano,
tak
ano.
první bude vzdáleně z toho Zoomu. Připojíme ho na můj obraz a on může mluvit?
No, toho možná můžeme připojit rovnou tady, ne? Ode mě. Já tak jako,
ano,
tak jako připoju vás, tak to je jednodušší, když já ho připojím tady tak a on prostě dá sdílení obrazovky a tak, jako, no, to jsem něco věc, no.
Jasně, jasně. Tak já ho vyzvu, ať si
Jak se jmenuje?
Jo. Navrátil, Jan Navrátil.
Jo, já mu musím dát možnost, já tady žádného Navrátila nevidím. Či tady má nějaký nickname nebo něco takového?
Vůbec netuším, já ho osobně neznám ani...
Takže dívejte se, jestli ho tady najdete. Jo? A když se tam najde ještě, tak se taky ozve.
Vyhledávání.
Navrátil.
Ještě zajímavé.
Já nevím, tak zkuste to stejně nějak hezky. Já zkusím tady teďka tohle. Tebe dám kohost. A ty si zkusíš teďka normálně share. Když máš share, tak bychom to měli vyrvat z ruky.
Je tady nějaký share?
Když rozepneš to okno celý.
To vypadá, že vidím.
Tady, když jako půjdeš, tak tady má dole.
Nejste náhodou pana Navrátil?
Ne. Počkej, tak já stop, já dám stop share, jestli ty tam nepomůžete. Jo, a teď když pohneš, tak ty dole měl vidět. To... Ne, to nechci. To je jiný. Já to koukám, že já když takhle pohnutím, tak mě tady normálně naskočí ta lišta.
Jo,
To
tam
máš
máš
tam?
tady někdo na, jo, to se vždycky bylo, ale to je tohle nějaká divná verze.
Potřebujete něco taky?
Ahoj, já bych jenom, jestli bychom mohli tweetně pustit.
Jo, seš na tom? Na Zoomu?
Ne.
Takže tvůj vedoucí oddělení měl za úkol nahrát si prezentace na svůj notebook a já bych ho teďka připojil a on by byl na Zoomu.
Tak,
já na svůj notebook nic nedávám.
Asistentka vedoucího mi řekla, že budeš promítat ty.
Já promítám, ale z notebooku vedoucí se připojí na Zoom a já mu tady mu to předám, jo, a on ze svého notebooku to všechno promítá. Jo?
Takže já se připojím.
Ty se připojíš
na ten Zoom, co přišel od Marcely.
Až přijde druhý takový jako ty, tak jsem zase já ho tady zpátky, tak 10 lidí.
Dobře, takže řeším
a už je tady najít. To je ten problém.
Aha.
Takže se přijde co nejrychleji připojit.
Jasný.
Můžu nazdílet.
Jasný.
Tak to k tomu panu vedoucímu, že se to pěkně připravil, úplně stejně jako v loni.
Ne, je to o něco lepší, než to bylo loni. Loni jsem neměl aktualizovaný Zoom. Tak je dobrý, když to odhalíme jako hodinu před.
No, tak já, co mám dělat? Dobrý. Jo, v pohodě. Já navrátil, už tady vidím. Já navrátil, takže já mu dám.
Já potřebuji jeden
Nejdřív, ale bych poprosil nejdřív, tak tohle máš. Připojit mě, že bys mu tak připojíte, když tak připojíte. Takže Adama Čermák, tady.
A teďka pro vaši informaci, vy se připojujete, já vás nepřiju. Já jsem vás teďka udělal hostem a vy teďka se rozhodnete tím zeleným tlačítkem share a v tu chvíli share.
Tak já jsem se připojil.
Takže já musím najít. No je tady třeba, vy jste měli představu, třeba 30 lidí a já musím toho člověka najít.
Jo, já tomu rozumím, že to není.
Kdyby to bylo 5 vedoucích oddělení, to by bylo pěkný, to není. Z toho vašeho oddělení jsem třeba měl 6 přepínání. Takže teďka byste měl vidět zelené tlačítko dole, když tím pohneš.
Já jsem ho měl i předtím teda.
Ale zvládnu si dobrovolně. No, není to vždycky jako bez problémů. Například jsem během toho zvládnutí zapomněl zapnout nahrávání třeba, jo? Takže já to špatně sdílím, tak počkej, ještě nikam mi nechoď. No, takže všechno je ještě vždycky za nějakou cenu. No? Jestli mi rozumíte. Tak co, vidíme tě? Vidíme tě?
Já?
Tady.
No teď se přihlásil tady někdo někde. No. Takže já do toho teď nechci hrabat. Můžu do toho hrábnout, jo? Ale
no, tak to asi bude fungovat. Jo, teď každý bude zvláštně share, tak už to bude. Jo. Já jsem si aspoň
nadechnout přestal.
A všichni to měli mít,
kolik se ten kontakt si
kontakt jsem dostal, ten člověk neodpovídá. Musím ještě telefon. Máte telefon?
Tak jo, a po telefonu.
Já ho mám.
Protože on mi neodpovědá na ten mail.
Jo.
Jinak, hele,
Všichni se mají napsat telefon?
Určitě. Všichni to měli mít prezenčně a proto ten pán teďka, co bude, tak ten to bude mít dále. Připojil se. 5 minut.
Ano.
Dobrý den.
Jedno je jisté, nic není jisté.
Thank you very much.
Ne.
Schedule. Paragraf se vyměníme koncem. No.
Okay, audience, I think we could start because it's on time.
Máš vedoucí oddělení. Měl nahrát všechny a připojit se na Zoom. Tak to měl věnovat nějakého zápisu. To jsem mu říkal. No, tak jo. Tak jo, můžeme začít. Prosím, posaďte se, ať můžeme začít. Ano, děkuji.
Okay, thank you. I think that we can start. So thank you to be here. My name is Adam Čermák, and on behalf of Professor Valášek, it's my pleasure to guide this session, which is focused on industrial production and automation department. Most of you already know that our department is divided into 4 groups and into two teams. First team and his main activities are in field of automatic control of system with time delay, and another team has the many fields, for example, the robotic applications, industrial robots, production machines, and manufacturing processes. Of course, we are solving in a lower test bed Industry 4.0. In this session, we would like to present 4 talks, and first 2 of them will be focused on the published papers in the last year, and another 2 talks, the last one, will be focused on the applied research with companies which were finalized in last year. So now I would like to give a word to the Jan Navrátil, who will talk via Zoom. So please, we will connect him And Mr. Navratil, please share your screen and the floor is yours.
Good morning. Okay, so that's something I haven't expected. I will try to share my.
We don't hear you.
Can you hear me or not? Hello?
We cannot see any on screen.
Yeah, just a second, please. Is it working now or?
Yes, now I can hear you from laptop, but that's not the solution because that's not the solution.
Excuse me. So what's the problem with the? Does my microphone work or? Hello?
Okay, we can maybe skip this presenter or let's wait. We will find solution.
Does my microphone work or not?
Once again, I will try it from my laptop.
Hello.
Okay, this presentation will be from the technical issues skipped. Sorry for inconveniences. Please, I will try to give the word to the Adriana Saldana. Is here? Okay. The floor is yours. Thank you.
Hello, good morning, everyone, and welcome to my talk. My name is Adrian Saldana, and I'm a joint PhD student at the Department of Instrumentation and Control in CIIRC and at KU Leuven with Professor Wim Michels, and in CIIRC with Professor Tomáš Vilidal. And I'll be presenting my results, which we had done in the 2 years in Leuven and in Czech, which is on stability optimization, which is applied to non-collocated vibration suppression. And this was published in the journal Mechanical Systems and Signal Processing. So, this is there a... Okay, so firstly, before I start with the main problem, let me first describe what we mean by absorption. So basically, we have a primary structure, say a building or a beam, and this structure is subject to harmonic disturbances of a known frequency. So what we do is to suppress vibrations of this known frequency, we place a so-called absorber, and we tune the parameters of this absorber such that its resonant frequency. I'm sorry, it doesn't work. So okay, I'm sorry for the. Okay, in any case, what we do is we have a primary structure, which you see is represented by MP, and we place an absorber directly onto it, and we tune the parameters of the absorber to match the forcing frequency. And of course, we are speaking about a real absorber, so we do not have a perfect absorption. And one way to mitigate this is by using an active absorber. And one such method in the field of delays is the delay resonator. But what we spoke about right now is the collocated setting. So you have a structure which is vibrating, and you can place an absorber directly onto it. In the non-collocated setting, because of practical reasons, we can't directly attach an absorber onto the part which is vibrating. And therefore, we need to place a sort of absorber remotely, as you can see in this figure. So we are targeting the mass M6 over here, and we tune the active absorber at a distant location, which is connected to M2. And so any control effort has to pass via the connected structure. And therefore, we need to take the entire structure into consideration. So one known way is to isolate the vibrating part from the resonant part by identifying a so-called resonant substructure. But this is not always possible if you have a parallel spring, for example. And with this in mind, we define our control problem. So basically, we have a system which is, in fact, our vibrating system, and we have a target which we want to cancel vibrations at, and we define our system in this way. And in addition, we also consider a non-negligible input delay, and we'll see the effect of this delay later on, and how we can also use it to our advantage, in fact. So we're using a simple control law for now, a simple output feedback. And with this, we have a closed loop system, which is defined this way. So once again, just to state our objectives, it's fairly simple. We want to make sure that vibrations at this target are completely suppressed. And secondly, that our overall system is stable. And we wish to maximize our stability by minimizing the so-called spectral abscissa function. And essentially, sorry. Okay, so for focusing on the vibration suppression task, we target the transmission zeros. And in terms of the stability maximization, we target the spectral abscissa function. So essentially, to explicitly target a single frequency, we assign a pair of transmission zeros on the imaginary axis. And in this way, the vibrations of this frequency are cancelled out at the output. But in doing so, we also change the dynamics of the closed loop. So we need to also make sure that our overall system is stable. And in case of our system over here, since we consider the delay as well, we must take into account that our system is infinite dimensional and we have infinitely many characteristic roots. And secondly, in this case, we need to check only that our rightmost root lies on the left half plane to ensure that our system is stable. And we push this to the left. So in doing so, we can formulate our constraint optimization problem, which looks like this. We minimize the spectral abscissa function subject to the constraints that the zeros are located on the imaginary axis. Okay, with that in mind, we should note that this objective function is non-convex and non-smooth. And so we need to carefully use solvers to optimize our objective function. And for our task, we use elimination. So we use it specifically because the system is the objective function is non-convex, and by using elimination, we ensure that our constraints are automatically fulfilled at all locations, at all search locations. So we consider two separate cases: the single input case and the multi-input case. In the single input case, we use the property that the constraints are in general affine in the controller parameters, and that way we can eliminate the constraints and formulate the same problem as an unconstrained optimization problem. And once again, we need to keep in mind that this is non-smooth and non-convex. And for solving the resultant problem, we use two main packages. One is TDS control, which is to deal with delay systems. And secondly, Hanso, which is a solver for non-smooth optimization. And secondly, in the multi-input case, additionally, we have the constraints which are polynomial in the gain. So the elimination in this case is not fairly straightforward. But we use the property that despite it being polynomial in the gain parameters, it's still affine in a subset of the parameters. And so we perform elimination by selecting the gain parameters from a single row and expressing it as a function of the independent variables. And finally, we optimize for the independent variables. Okay, with this in mind, we move to experimentally validating our control design method. And this is our test setup in our lab. So essentially, we have a system which is excited upon by F. It's not very clear here, but it's on the right-hand side. And we wish to target the mass which is at the center using two inputs, U1 and U2, in the multi-input case, and just U1 in the single input case. Okay, so we first create a model of the system, and we apply the method which I described before. And from this, here as we see, we have the open loop poles and zeros. We see that our system is inherently stable, but the zeros are not precisely on the imaginary axis, which means that there is some kind of, these frequencies are not damped. And by parameterizing our controller using the single input case, we explicitly place the transmission zeros on the imaginary axis, and we minimize the spectral abscissa function, which you see is at around -5. So we ensure that our system is sufficiently stable. And the same for the multi-input setting as well. And with the multi-input case, we have more free parameters, so we have a better spectral abscissa. And finally, I have a small video of what this looks like. But I'm not sure if, do we have time? So in the first case, we are looking at the single input setting. We have an external disturbance, which is on the right-hand side, F. And we're using just one actuator to suppress vibrations at the central mass. So now there's no control, and in 1 second control, and if you see the mass is completely stationary, using just a single input. And the same is also for the multi-input setting. Okay, so that was it for now, and based on the same method, we've kind of moved forward and yeah, using the same approach, we've used a single input, and we've implemented it on a dynamic delayed feedback controller to target multiple frequencies, which is in fact one of the state-of-the-art problems. And as you see in this figure, we have placed 4 zeros. We are targeting 4 frequencies, and yeah, we've used the same method, but we've used a delayed feedback controller. And yeah, that's it for me for now. Any questions?
Okay, thank you. One short question from audience. So, can you see any potential direct application of your model directly in the industry?
Yeah, yeah. So basically, our model is based on robotic manipulators, where we can't place an absorber directly. So the head of a spindle, for example, and our idea is to use absorbers which are which can be parameterized remotely to suppress it at the spindle head. But right now, I'm not working on the practical model. We are working on more of theoretical.
Okay, thank you. Any question? So let's thanks again to our speaker.
Thank you.
So, and this speak will be led by me because from this group I'm responsible for ultra-short pulse laser processing. So in this case, I will present you some contract research with company which leaded to a successful application. For those who don't know us, where we are in the lower test bed, we are directly in the corner. This is a booth for laser micromachining. If we look inside of this system, we can find out that it's equipped with 2 laser sources and a multi-axis kinematic, 2 galvo scanners, cameras, etc. The most important thing is that we have 2 sources. One is short pulsed and second ultra short pulsed, which is placed on the top of this optical board. These 2 type pulses we can combine, and we can define different behavior of the interaction between material and the laser beam. If we look at this graph, there are some areas of the laser applications which correlates with the pulse duration. Looking in the micromachining applications, we have 2 areas. If we apply the same amount of energy, the average amount of energy, we can get different results, because if we shorten the pulse duration, we are getting a different maximum or peak energy, let's say. This causes that the behavior is different, and the transition between the transition energy between heat and ablation very differs. Looking at final samples created by short pulse and ultra short pulses, you can see that there is different, let's say, chip breakers fabricated on cutting inserts, and the there are obvious differences in quality, surface roughness, and we are not talking about this type of machining, but it's obvious even in different type of applications. If we look at the first case where we are cooperating with many companies, for example, one company is European Cryogenics, who is creating these shafts for compounders and other things, for example, gas liquefaction. We were fabricating these grooves, which has quite big requirements on the reach depth, plus minus half micrometer, and the final roughness and the final position. Okay, we already had some technique, some technology, but the substitution by this laser micromachining was beneficial because of the system and the technological benefits, where we can get good repeatability, productivity, and small dimensions. Another case where we are doing laser stripping or decoating of thin layers, we can apply it, for example, for manufacturers of cutting tools. For example, Dormer Bramet wanted us to create some laser stripping without any affecting of the substrate material. In this picture, you can see that there were created some stairs, and there is some interface between the thin coating and the substrate without any residues of the thin layer. The final application can be done for watch industry, like this example, or the tool industry. In this case, we can have a profit from this technique because we can do it in selective way in terms of that we can erase certain type of layers from the multi-layer system, or we can create only local stripping of all thickness of the layer. So that's it from my part. If you have any question, I will be glad to answer you. Yes. The first company was the European Cryogenics, and the second one was the lower tenths of pieces. But there is, in the case of this company, if we are talking about the Dormer Bramet, who is manufacturer of cutting inserts, we are talking about thousands of pieces in case of implementation of this technology. Yes. We completely did this technology and developed this technology from zero to the production process, because it's not in many things it's not certain how it must be done or how it must be the procedure. We did some optimization. We did some from, let's say, from the beginning, from the ablation threshold testing to see where we can go to the with the process parameters to not avoid some subsurface structure of the material. And if you need to go to the productivity, you need to find some equilibrium in this, and that was our main contribution. We can talk about it later. Okay, I would like to invite next speaker. Mr. Štěpán Chádek will tell you something about special functions of laser cutting machine control system. So, place is yours.
Thank you, Adam. Good morning, ladies and gentlemen. I'm going to present a second case of industrial cooperation, of industrial research with Czech company, Czech producer of laser cutting machines. Laser cutting, it's an industrial technology which is based on laser to vaporize material. The principle is quite simple. You need just laser source, optic path, cutting gas, and some cutting head, which is maintained in a constant distance over the cutted workpiece. On the left-hand side figure, you can see a sample of laser cutting. And you need to assure that the nozzle it is within a constant distance over the cutted workpiece. The special functions which were required by the Czech producer can be summarized as follows. First, increase the cutting efficiency. It means decrease the time of cutting. And second, probably the more important, it's collision avoidance. On the left-hand side figure, you can see a sample of metal sheet in industrial production. It consists of tens or maybe hundreds of small workpieces. And these workpieces, they are not cut in the row one after another, but the location is skipped with respect to decrease amount of the heat concentrated in the metal sheet at the time. So the machine still skipped from one location to another. And on the right-hand side figure, you can see a sample of a stuck workpiece, which can cause a collision, and very often it causes a collision. So this is the motivation for special functions integration. The special functions implementation required a hardware upgrade as well. It means the proportional valve responsible for constant pressure setting, the laser source, and the most important cutting head. The new cutting head has a great benefit with a large distance control range. It enables 80 millimeters distance control compared to original only 20 millimeters range. Okay, and how does it work? So, about the increase of cutting efficiency. The efficiency is based on the 3 points. First is Pierce positioning optimization. Pierce means the initial phase of cutting. You need to position the laser to initial position, start the laser, go through the cutted workpiece, and then you make the movement. And we use a distance control within this moment. On the left-hand side figure, you can see some scheme of the original and the new situation. In the original one, the laser cutting head move up in the Z direction without distance control, move in the XY plane to the target position, then move down slowly without the distance control, since the distance control range was only 20 millimeters, and then with the green arrow mark, the green arrow marks active distance controller. So we modified this procedure with as follows. We still got the distance control on and move with the direction only in XY plane, and the distance control enables the Z-axis positioning. You can modify the gradient of this movement for the user. We select a 10 scale grade, and if you select 0, you copy just the original path with the difference that the distance control is still on. It means it still checks any obstacles which are on the metal sheet. On the run head, but there were some problems with the current installation, because there are hundreds and hundreds of G codes which are not able to be modified at this moment. So the customers refused us to modify these G codes. So we decided to implement our internal post processor, which can be enabled pressing a soft key like we call it ping pong. It simulates the movement. It's quite similar to ping pong game, you know. And if you select this functionality, this internal parser is code, it modifies the G codes, but the user still see his original G codes. The development, commissioning, and testing was fully performed in our laboratory in so-called lower test bed, which enables full-scale testing. It means air conditioning with filtering, commissioning, accessories, connection, and so on. You still can see this laser cutting machine at the same position like on this photo. On the right-hand side figure, you can see the active distance controller. I hope the video will go on, yeah. At this moment, the z-axis from the controller is constant. It keeps the constant, hold the constant position, and the movement move up and move down within the z position is based on distance controller. You can find some videos when the operator puts his hand instead of a screwdriver. I was not so bothered to do that. Okay, and last point of this collaboration was implementation and the contractor, where the hardware and software was transferred to the contractor's laser cutting machine. We received 5 days to completely upgrade and update the control system and the hardware, and we did it as expected. Increase of cutting efficiency was proved, but to say how much was the efficiency change, it's quite, it's not easy because it depends on G code. Roughly speaking, the more workpieces you cut, the higher efficiency you get because you can skip from one cutted workpiece to another in a shorter time. And on the right-hand side figure, you can see a sample of the first cut workpiece, and fortunately, it got stuck like that way, and this updated control system skipped over without collision. The collisions is, of course, very bad. It's time consuming for the operator because he had to change the nozzle, change ceramic adapter, and recalibrate this laser cutting head again. So collision avoidance was very well acknowledged. So thank you for your attention. If you got any question, feel free to ask. It's a fake cut. It's not so high. At this moment, they got about 20 installation in the Czech Republic, and it's just a customers. It's always a customer solution with some special functions like that one. So at this moment, about 20 installation. Thank you.
Maybe one question from my side. What is the highest range of this allowance for this sensor?
80 millimeters at max.
Nice, thank you.
Thank you.
Thanks.
Now, the Department of Intelligent Systems.
So, still good morning. I am very happy that we are within the time schedule.
I would like to introduce a little bit 6 presentations which were prepared by members of our Department of Intelligent Systems. First 3, as a matter of fact, the department consists of several bigger or smaller groups. The first 3 presentations were prepared by the group of Peter Cadera, who concentrates the efforts of this group to optimization, planning, scheduling, simply industrial applications. The presentations will be given by Martin Macáš, by Václav Jirkovský, and by Sára Strakošová. It's a PhD student which will present her interesting presentation from conference. And then the group of, let's say, nuclear physics, I would like to say active and partially radioactive. Group of Professor Škoda will present their new achievements. Tomáš Kořínek will do this. We will follow with the group of Ondřej Mamula, which is focused on control of energy systems, power plants, and so on. And you have had already part of this presentation by Mr. Šucha earlier. And the last, but not at least, presentation will be given by Jan Šedivý, who is the lead of speech processing team. So he will concentrate his efforts on building LLM. That's very hot topic of today. So you can see the very broad scope of interests of this department. I am giving the floor right now to Martin Macáš. He will optimize in his presentation waste treatment.
Okay, thank you very much for the introduction. Hello, everyone. My name is Martin Macáš. After those laser cutting and laser machining topics, I have slightly less sexy topic of waste management, but every little boy wants to be a dustman, so maybe it will be interesting, slightly at least. So I'm presenting a test before invest service, which we provide to Municipality of Prague under EDIH framework. By the way, it's actually, okay, maybe next slide, please. It's actually a very good use case. Yeah, very good use case for applying machine learning or data science, AI, because the municipality already has a lot of data. 7,000 containers are equipped with fill-level sensors, and they really want to use it because they invested already. So we have data for like 1, 2, 3 years already prepared. The data infrastructure is already prepared. So everything is ready for applying those methods. And you can see here an example of signal, which is quite simple. It's just a fill level time series for each container. So this is one example. You can see the drop downs of the signal, which are the collections of waste. And I should show the whole flow chart, let's say. So on the left side, we can see the fill level sensing and data storage. The infrastructure is prepared, as I said. And what we do is actually should be on the right side, the final some decision making based on data. The decision making can be, for example, reporting. So sending some reports to sensor providers, some reports to collectors of the waste, the collector companies, or rescheduling the collections statically or dynamically. I will speak about that later. The dynamic optimization, the routing of vehicles that collect garbage is not part of the project, but will be future work probably. The main objective is to make the waste collection more efficient. I'm sorry. Make it more efficient. But to do that and to perform a good decisions based on data, we need a good data. So in the middle, you can see data interpretation cleaning. We have to make data more trustworthy and more correct, and to interpret them and find different things, different mistakes and errors. So this is probably the most important part of the whole current project. Here you can see what we can detect, what can be the problem. Here is the simplest case of detection of data waste collections, which you can imagine is simple. But there is one false positive point, which is caused by error of the sensor, and those errors are normal. It's not so something very not so very rare. So it can lead to some problematic decisions, like the container. There was extra collection of the container, which is not true here. So this is an example, but there are many such examples, and I don't have time for them. Okay. Here are some other things that we need to detect, and we are using heuristics. We are using also pattern classification, supervised learning. On the left side, you can see, for example, stuck entry of the container, which can be a problem for citizens. In the middle, you can see different peaks caused by error of the sensor. On the right-hand side, you can see a waste slide, which is normal, but we must differentiate it from sudden drop down, which are errors of sensors. So those are just little examples of many things that we have to detect. And behind those, or except of those, we also need to detect some other abnormalities. So we are performing also anomaly detections. Here is a very simple example from of a method well known from industry of Six Sigma anomaly detection, where we have like a weekly profile, mean weekly profile, and we have some standard deviations, and we define a range of plus minus 3 sigma 3 standard deviations. And if some point exceeds this range, then it can be anomaly. Here is probably anomaly caused by first school day. But we also tried to test different other methods. The best performing method at this moment is based on autoregressive model with exogenous variables, where the exogenous variable is the collection signal, so a binary signal, where we threshold the error of the forecast of this model. But we also use autoencoders and threshold the reconstruction error of that. And we apply and test many of those things to choose one of those for further integration into a Golemio system, which is Prague platform. Okay, here you can see how we are trying to simulate what will happen if we change the schedule of collections. This is very simplified, by the way, but we have the clean signal at the beginning. We can compute its difference, and then we can remove the collections. And then this represents the deposit of the waste in every hour. And we can use it by cumulative sum together with the new collection schedule. We can use it to simulate the new schedule, the new fill level behavior. And we can use it in an optimization loop to optimize some criteria. An example is here. You can see that we can also simulate how much of the waste will not be deposited into the container because the container is full. It's the green part where we can measure the mist capacity and overflow, and we can also measure how often and how much the container was collected without being full, which means that we unuse its capacity and we waste fuel for collections or CO2 and so on. Both those criteria are in trade-off, but both have some ecological gains. It means on the left side, we save fuel and reduce CO2. On the right-hand side, we reduce the pollution of neighborhood of the containers, for example. We have some KPIs, which I will not go into deep details, but first are the data cleaning KPIs, where we are able to automatically analyze the signals instead of manual analysis by expert. There are also optimization KPIs where we are able at this moment reduce those criteria by 10%. This is measured on 100 containers. And there are many other benefits which you should see here. Also, for example, I must point out the networking because it enables better communication between the municipality and the other stakeholders like citizens, but also a collection company or sensor providers. And we had to develop an application which will not be used finally, but it's used for enabling communication and getting feedback from the customer, which can give us feedback about the methods, but also user experience, but also we can use it for evaluating the methods in terms of comparison of our predictions to what really happened to the real annotations. And those are examples. The user can optimize methods, can go through the signal, can optimize schedule of collection, can annotate data, and can observe the automated annotations. Okay, thank you very much. This is last example. This is a predictive maintenance case where if we detect a lot of sensor errors, we can predict that the sensor will die soon. So this is like 3 weeks ahead prediction of sensor death. So this is another application of this. Thank you very much. Finally, it will be selected methods will be integrated into Colloquium system, which is already existing. And that's probably all. Thank you. Questions? Not yet. We will do it. Thank you. It's a nice suggestion. We didn't do it yet. We applied just 4 methods, and we didn't try to compare them. Combine them in this sense. So we will definitely do it. Thank you. Thank you.
CIIRC, we are 4 minutes behind the schedule.
So, okay, hello everyone. It's my pleasure to introduce or give you an overview about our project, contractual research with Škoda Auto Company. And the project was about the weights of the special car equipment. So, for the first, some background to understand the entities from the next slides. Most of us have a car, and most of them, for example, me as well, have a car from Volkswagen concern. And maybe you can find in your car in a service book or on the tank cover, you can find the car specification. It is composed of approximately 200 families of PR numbers. PR number represent production order number or production or product specification or part specification. For example, a GOC represents 5-speed manual transmission. So everything in your car is specified by a PR number. And when you compose all of the families, you have a complete specification of your car. Sometimes the PR number represent nothing. For example, You have a pair number for the car without sensor, next pair number for the car with a front sensor, and the next pair number from the same family represents both of the sensors from the front and the rear side of the car. Next, we have a regles. It's something like a rule which tells you if this pair number from this family is used, then you have to use some other pair number from the different family. Okay, the target of the project was to estimate pair numbers weight increments with respect to the weight key. Weight key is represented by 4 families: the family of the engine, bodywork, transmission, and the last one is the equipment lines, I think. And the ultimate goal was to optimize overall process, because this process was conducted by one person, and typically it is relatively time consuming, and he spent many hours during the weight specification, and it is difficult after some upgrades of the parts to do it again and again. So that was the goal, or the main goal. And also it is not just I don't want to how to say it, just a pleasure for the Škoda company to predict or estimate the weight of the car, but it is caused from the legislatives, because you have the rule that the estimated and also produced car dispersion should be somewhere around 5%. They are really good in the estimation of the weight. They are somewhere around 3%, but still they have to be better in the precision. So the biggest issue is that it is not possible just to sum up the parts which belongs to the pair number, because when you combine different pair numbers, you have different parts. So to solve the problem, we use a SAT solver. We model all of the regles which are available for the car. There are technical regles, active regles. Technical, for example, if you have one type of engine, you have to have specific transmission. Active regles, like you have a car which is produced to the Sweden, you have to have a battery with a bigger capacity, etc. For example, for one car, it is around 12,000 of regles which specify or limit the given production. And we use a SAT solver to generate feasible car specifications and also select, they call it in Škoda Auto, weight relevant pair families. So I have already mentioned that the car is specified by weight key, and with the help of the regles, for example, 40 till 80 other families are dependent on the weight key, and the rest is the thing what is important for this project, or is input for us. Next, we implement something we call it weight dispersion analyzer, and I will give you an overview of the main steps. So for the first, we generate a set of pair numbers from weight relevant families. Next, we prune the solution space using a database, bill of material database in English, I hope. And next, we go to investigate these pairs from a family to get a weight contribution. Next step is to generate identical feasible combination of pair numbers. So the car specification for the pairs from the previous step. Now you can see, so the outcome will be better with or became better with increasing number of such pairs pairs of the car specification for the pair of the pair numbers. Next, we compute the weight of overall car, and then the weight difference between these two cars with the same specification, but just with a difference in the given pair of pair numbers. We have the weight contribution, and after, I think in this step, we generate 10,000 this pair of the car specification for every pair. And at the end, you can see the dispersion of the weight contribution, which is provided here on the in the figure. And there are some limitations that if the dispersion is bigger than some threshold, you have to specify or improve the dispersion with the usage of the additional pair number from different family. So in this step, we go through all of the other families to find out suitable one which provide the smallest dispersion. So to conclude, the solution was not limited or was not limited just by the target, but also it is limited by the processes in the companies and the systems and softwares which are available. So it means that the outcome was, for example, Excel sheet with a specific number of the lines, the most important contributions of pair numbers, because these contribution of the pair numbers is manually added to another system, etc. So thank you for your attention. Sorry. Yeah, it's mainly the problem of the generation of the car specification, which are feasible, and also the steps like you have a car specification and you would like to ask if it is okay or not with respect to the regulations. So, thank you.
So we are 5 minutes behind the schedule, and the next speaker is Sarah Strakoshova.
Good afternoon. Good afternoon. Yeah. I would like to present you my first publication at conference IEEE Indian last year. The name or title of my publication is Product Digital Twin Supporting End-of-Life Phase of Electric Vehicle Batteries, Utilizing Product Process Resource Asset Network. So the motivation of our work is actually something we encountered ourselves when we wanted to create a disassembly process for EV batteries. And the problem is lack of support from manufacturers for the end-of-life processes. To address this problem, we proposed a product digital twin, which for us is a digital replica of a physical product. So in our use case, EV battery. This digital twin accompanies the product from initial design to recycling or reuse, and it offers insight for each product based on its condition and usage history. So this digital twin offers lifecycle management for a product. To create such digital twin, we are introducing BIFLOW Product Process Resource Asset Network, which is a graph-based model extending the traditional PAN approach. We can see a generic model here. It combines products, the red ones, processes, green ones, and resources, combines them and creates workflows, which in a classic PAN approach is more like just for manufacturing, but we extended this approach in bidirectional flows for both assembly and disassembly workflows. Since we also know what processes need which resources, this approach can also support flexible and efficient planning for manufacturing and second and end-of-life operations. Key features of BIPAN is the bidirectional operation, as I already said. So integration of both direction in just one model. It supports forward the assembly, which can be manufacturing, and also the backwards disassembly, which can be recycling or remanufacturing for secondary applications of product. And also it enables design of repair workflows, which combines assembly and disassembly. Also, it complies with industrial standards like ISO 95 and also the automation ML. Here again, we can see a simplified model of EV battery, BMW E3, in automation ML. So we created the BIPAN in automation ML, so it's readable for computers and for manufacturing systems, etc. And of course, it supports the creation of the digital twin. Now, I would like to demonstrate a repair use case, which I find most interesting. Here we have the whole BIPAN for the simplified EV battery. And this is the workflow we are following. So first, we are moving in disassembly way, since we reach the part when we can remove the damaged module and replace it with the new one. And then we move back in assembly way until we have, again, the whole EV battery. So to sum up, BIPAN-based digital twin for products provides efficient planning for several operations during the whole life cycle of a product. Yeah, thank you. That's all.
Questions? Not yet, so thank you very much. And let's go to the next speaker. And that's Mr. Kozinek. The presentation is very well. Perfect.
Okay, so hello everybody. My name is Tomáš Kořínek, and I'm from the group of Professor Škoda. And I'm going to present one of the results of our research. And it was focused on multi-physics problems in nuclear reactors. And this is something we are doing under one project, which is in National Center of Competence. It's a Center for Advanced Nuclear Technologies. And where we have a sub-project which is focusing on some high-fidelity simulations using couplet codes, which we like to use for validation of macro codes, where macro codes are nowadays used for safety analysis of nuclear reactors. So this is the work which was published in one of the top journal, Progress in Nuclear Energy, and I call it, it's a swing journal because sometimes it's D1, sometimes it's Q1, nobody knows. But it's one of the best we can publish there. In this case, we did some multiphysics, so it means that we coupled two problems. We coupled neutronic physics with thermal hydraulics. There are several reasons you need to couple it because there are some feedbacks or strong interaction between each other. So what does it mean? Basically, what is going on with the fission and nuclear physics in influence of the results we obtained from the thermal hydraulics. So it means that fission is influenced by temperature, density of the coolant, fuel, and so on. And because of this strong feedback, you can reach some problems with stability of the calculations. So that's why we focused on relaxations of those calculations and see what's the influence on the computational cost and accuracy of those simulations. So why we care a little bit, why we care about focusing on some computational cost and some accuracy? Because, for example, nuclear reactor core, if we speak about reactor we have in Dukovany, you have more than 300 fuel assemblies. Each fuel assemblies contains 126 fuel rods, and fuel rods is composed with a fuel pellet and cladding, which basically encapsulate the fuel, and this is surrounded by the coolant. So it means that in the reactor you have something around 40,000 fuel rods you have to calculate. So for the Monte Carlo simulations, you need a lot of particles to simulate it, especially if you have 40,000 fuel rods. So in our case, we take a look on simple problem. We took one of the fuel rods, which was surrounded in the coolant, and we performed those couplet calculations using high fidelity code. So for thermohydraulics to CFD, and for the neutronics part to Monte Carlo. And we take a look on the relaxation. As I said, there are a lot of strong feedbacks. So when you start to do it without any relaxations, you will basically never converge because there will be some oscillations in the solutions. So in this case, we focus on methods of the relaxation. So there are different methods using some constant relaxation factor, some factor which is changing during the iterations, and also some additional change when we increase number of simulated particles, basically to save some computational time. So basically, one of the results we take a look, because from the Monte Carlo simulations, you have some uncertainty of your results. So we observed like what is the change between the simulated particle, those simulated particle histories, and how it will influence the uncertainty we are receiving from our simulations. So we saw that the most important, it's not linear. So it means that after some time increasing of particles, you will achieve some stable uncertainty. And another case, when we compare different relaxation method, we saw that for some combinations you can reach convergence quite fast, but also it's after some cost. So when we start to change some particles, so we achieved basically within few iterations, but because number of particles influence the computational cost, so it's not so. It's important to take care about not only a number of iterations, but also computational cost and especially the accuracy. So just one example on the right side, there is a cross sections of this fuel pin. So on the left. There are after first iteration, so top is when we use the large number of simulated particles in the first iteration, and the down left is when we used not so many particles. So you can see if we are not using a lot of particles at the beginning, so there is a high non-uniformity because of we have poor statistics for this. But within a couple of iterations, you achieve quite better results in this case. So that was one of the outcome. As I already said, if you have something around 40,000 fuel rods, and this was the case only for one fuel rod, and we still spend like 200 minutes. So even if you are using some high performance clusters to perform those calculations for the whole 3D model of the reactor core, we are talking about weeks, especially for the multiphysics, maybe months. And that's one of the focus on the study. Take a look on a simple problem, and results will be propagated on those large scale simulations. So that's all from my side. Thank you.
Thank you. Nuclear question. Yeah. From Germany. Yeah.
Former colleague of mine did water physics simulation.
To be honest, I'm like thermohydraulics, so I did the other part, but for the Monte Carlo, I know that there are several methods how you can improve it, also using machine learning. But usually for our case, nuclear industry, it's quite rigid. So that's one of the case. So sometimes you have to stay low.
No, věří.
Great. So my name is Ondřej Mamula. I'm head of energy group under Professor Mařík, and I will present you a success. We call it success story of research and development made in our department. Okay, it's wrong direction. Last year on this spot, I presented that we had developed an algorithm which will be implemented in the real application. Since then, you might have read, the time passed through the winter, early summer, into the summer, and then maybe in June or July, I think you might read some articles about the go live of the power plant, and there was several official starts and conferences on the spot presenting that the investor achieved this goal, and the operation was put in the power plant was put in the operation. What was the timeline of the project? We met with the investors approximately in 2019 and started to think about their concept. We provide them with the initial feasibility study, providing insight if one big engine or more small engine are feasible for their idea of provision of ancillary services. And then we came finally to the solution of 6 small engines and the battery system, which seemed to be ideal. Then was a not paid time of the idea so growing, within which we pushed the investor to go with us into the project supported by the Technology Agency of Czech Republic, and the algorithms has been developed within this project. Not at the end or after the end of this project, but within this project, we have started the implementation because we had to put the prototype of the algorithm into industrial application. And in July 2024, we started operation. On 15th of July, we went into real operation, and in May we successfully passed with the first generation of the algorithm certification. So we were certified that the algorithms is compliant with the rules of TSO on provision of ancillary services. And then we implemented some missing parts, and we started the operation. The power plant since then is in full operation on 30 megawatts. Nowadays it was get up to 35 megawatts of power provided within the ancillary services, and we have not any stop or malfunction caused by the algorithm. So we are, I think, successful from this point of view. I will quickly respond to the question about the money which are connected to the project. I just remind you what's inside the power plant: 6 more generators driven by aeroderivative gas turbines, accompanied by battery system. In total, it's 55 megawatts, but we combine it up to 35 megawatts to keep some quality rules of the provided services. And the system, the control system, is embedded into the Siemens system. Our algorithms works as a Docker container and is composed by several autonomous pieces of the algorithms, which tries to interpret the commands from the TSO, tries to find the best number of machines to be run, checking the healthiness of each component, and maybe stopping to command them and asking for another one. And we are still developing the pieces of the algorithms to increase the efficiency of the control and increase the robustness of the control. In terms of money, I will get back to the timeline. I'm sorry. In the term of the money, on the implementation, the implementation was supported by the contract with value of 3 million crowns. Now we are negotiating about the follow-up contract in enhancing the services for next 1.5 million crowns, and on the table are other features which might be in 2 or 2.5 million crowns within year 2025. So I think this is a really big success of R&D implemented into the real operation. If there is a spare time, I can show you instead of digital twin, I can show you the real operation of the power plant. So I'll try to connect. Okay. Tak asi se mi to nepůjde. Okay, so next time, if you are interested in, I can show you the real operation of the power plant, because I'm right connected. I'm right now directly connected to the control system of the power plant, so we can see what's happening inside. Just to imagine or help you to imagine what money are we talking on the investor side. And I say our because I'm from the 1st of January are on part-time job within the investor responsible for the operation of the power plant. So the best 15 minutes we made within the operation of the power plant was time when the regulation energy, which is produced by the power plant, was the cost of the regulation energy was 12,500 euro per megawatt hour, and on full power on 35 megawatts within 15 minutes we made 2.5 million. If the algorithms would work bad, we might lose 2.5 million, because the penalty is approximately the same size against the revenue if the power plant doesn't work well. So this is the business we are working in. It's really tough and sometimes is exhausting, but I think that we are proud that the algorithm is working for more so half of a year without any malfunction. Okay, thank you.
That, for example, in other companies, they are going from gas turbines to batteries, and then from batteries to grid, right? And here you don't have those losses, right? Maybe that was the question of Radia. What is the profit of your solution compared to?
Oh, technical profit. Okay. Well, the conventional way of ancillary services provision is a spinning reserve. So there's a big power plant, for example, 100 or 200 megawatts, which is not sell fully to the market, but there's a spinning reserve 10 or 20 megawatts, which are regulated by the TSO or respond to the regulation from the TSO. It usually is coal-fired power plant. So if we need to want to decarbonize the energy system of the Czech Republic, we need to skip those power plants and replace them by something else. It's hard to regulate solar power, the wind power. It's not impossible, but it's limited somehow. So we came with the solution of a standby power plant, which provides only ancillary services, doesn't provide the power to the market, to the grid, to the market. And we try to combine the technologies to achieve the high efficiency. If the battery is charged by some generator, the efficiency of the generator in this case is around 30%. Efficiency of the battery cycle is 80%. So we are around 24-25% efficiency in total. And the algorithms try to provide the electricity directly from the generators into the grid. So we are increasing the efficiency only in specific states when the machines are starting or stopping or some intermediate course of the demand from the TSO. We are using the power from the battery to bridge those short episodes. No, we are. This is the business of ancillary services based on. It's not a spinning reserve, but on a reserve. So there's a reserved power of the power plant, which is paid by the TSO. For example, 20 euro for each megawatt an hour of the reservation, and needs to be prepared to provide something between zero and the full power. So this is the first stream of the income from that business, and then the TSO sends a command. And the reaction is specified in the TSO grid code. So we know that we have 5 minutes, up to 5 minutes, to achieve the requested command. The command might change every second. We don't know when they call. We don't know the power they call. So we need to be ready to realize the power under any circumstances. This is solved by the robustness of the control algorithm. Yes, we can, but our goal is to make the response of the control algorithms transparent, and from the point of view of the dispatcher on the TSO, it's better to give, say, predictable response. If we push the battery to full power, then wait and then take some power from the engines, it's somehow weird realization which might get the dispatcher confused. So we are trying to achieve the linear release of the power under any circumstances. But technically it's possible.
No, then thank you once more. Bude to od Petra z notebooku. Super.
Hello, everybody. My name is Jan Šedivý, and I am running here a small group working in the NLP. So I'll bring you from the massive money and big energy to very software-like area. But as you may have noticed in the news, this area is also spinning enormous billions in the US, billions of US dollars. And it is really developing very fast. So let me first tell you something about our department.
In the last year, actually, many students who were working with us for several years left, 2 PhD students and some other MSc, etc. So we are at the moment restructuring the group and looking for new people working with us. We were left with only 2 PhD students, and another student is joining us next month. And we have several contributors from the staff members from CIIRC. And while changing the staff, we are also opening new areas. And as you may know, we have been working for several years with Amazon, and we were competing with our dialogue systems. So now we are continuing to work with Amazon on a new task, which is developing language models, generating Python code, but ensuring not to generate malicious or vulnerable code, meaning that if you would ask how to do DDoS on CNN, we must reply, no, we don't allow that. We won't generate anything. Just to complete this page, I just skipped the partners we work for or we worked for in the last year. As you can see, we had several business partners, starting with Porsche, Seznam, T-Mobile, and currently we work for a Ministry of Finance. All these cooperation with these industrial partners are thanks to what we have done in research, because what we deliver to these companies is basically what we started to work on 2 years ago. So currently the Ministry of Finance is a retrieval augmented generation system using several algorithms which have been partly developed here at CIIRC, and the combination of these algorithms or the whole architecture, it was fully developed here, and we are now in the phase of deploying it and testing it. But let's go back to what we will do in the, oops, I have to do it the other way around. So the Amazon Trusted AI. So as I explained, the basic idea is to generate non-malicious code and not only show the code, but also to explain how the code has been developed. There are already applications on the market, like which you can definitely install on your machines, like Copilot, and some other businesses are developing these systems. And the basic idea or the basic way how to make sure that we don't listen to something which has some not very politically correct idea is to create a system which is depicted here on this picture. So there is the question, and then the first thing we do is we use a smaller language model which has around 1 billion parameters, and this language model is used as a classification machine, meaning that we have only one output, and the output is a probability of the answer being correct or being incorrect. Based on the correctness, we decide whether to call another larger language model, in our case around 8 billion parameters, and we generate the code if the question is okay, and if the question is considered to be not correct or to be malicious, then we call the LLM with a different prompt and ask the system to generate something like, I apologize, but I cannot generate code like this, etc. So this is the simplest way, and most of the, as far as we know, because not everything is published, most of the developers are using very much the same scheme. So our task is to first of all, train or design set for training the classifier, and then design set of tests of training sentences for training the large language model. Luckily enough, we have, thanks to AWS, a lot of resources on GPU cards, so we can actually use a lot of time and train it. But the key question is, do we have the right training sentences, meaning having the test which really shows good Python code and not very good Python code, and how to use these training sentences to improve our language model. These days, many of these training sentences are generated by language models. So we are developing now these days systems for generating training sentences. And it is well known that these synthetically generated training sentences are further improving the LLM, which was generating it, which is recursion, and this may ultimately lead to singularity or creating systems which are better than humans. And currently it's a hot discussion or hot topic discussion on all these social networks, within what time we would reach the singularity. So this is our program, or this is our vision for this year. And certainly the main vision which is behind learning how to develop these things and how to research new systems or better systems is to actually develop application which would help our industry here in the Czech Republic to make many of their activities, specifically the administration activities or activities processing data, how to make them more productive. This is what we are doing these days in the Ministry of Finance, and keep us your fingers crossed so as we succeed, and it will bring us new partners and new opportunities. Thank you.
Secondary language model with 1 billion parameters. You actually classify whether the generated code from the main LLM is malicious or not.
Well, that's another possibility. So you can check the code, or you can do post-processing as well as checking what the users are sending or requesting to generate, because typical way how to make the LLM to generate malicious code is to show it some already malicious code and asking the LLM to improve it. So that's correct. We do the check at the beginning as well as in the end. Sure. Yeah, absolutely. There are so many ideas. There are systems who do these days chain of thoughts, and that's precisely what you suggested. So there is one LLM which can do it from the end, from the beginning to the end. Like there are examples of how to count the number of R's in the word of strawberry, which is a classical example how people are testing it. And the latest DeepSeek, if you try it, is for free. Then it generates a whole line or series of thoughts how to calculate it and correct itself and so on. So we can take it offline. There are millions of things. It's really exploding. It's unbelievably going everything fast. It's hard to even track it. Absolutely, absolutely. I am talking to Honza. I don't know if he is Hula. So we are in contact, and thank you. I appreciate it.
So my question is, wouldn't it lead to some qualitative decrease in this artificial text?
Yes, lots of discussions. Our observation is that it is further improving the model. Certainly, you can do the teacher student scenario. So the teacher can be like Claude or any of these best models on the market. But there are articles proving that even the same model teaches itself, which is the recursion I meant, and this is what may lead to singularity, because the model is improving itself. And there are lots of other things, but we don't have, unfortunately, time. But yes, that's good.
Come back at 20 past 1 and please be on time, right? Už je tam máme. Jsem dobré obrátilo nakonec. Zase toho strach. Možná bude i opět. Ten strach trošku chtěl dobíhat. Tím na oběd do Respiria, no? Respiria. To dopadlo. Nic. To máte pěkný článek, jsem viděl, no, že bych to mluvil, ale jako vypadá to zajímavě.
1, 2, 3.
On this, and now we will start with Department of Artificial Intelligence. So, please, Joseph.
Oh, thanks. Hi, everybody. I will say a bit about what the AI department was doing last year. So we are 4 groups. We are the group of machine learning led by Robert Babuška, foundational AI led by Tomáš Mikolov, then formal methods led by Mikuláš Janota, and automated reasoning led by Martin Suda. Last year, we were in a bit of a funding trouble, which looks like kind of getting better now. So we have actually grown from 18 people to 24. We have like 6 more people now. We supervise or co-supervise roughly 11 students, one defended in 2024. You will see 4 presentations of 4 papers in total. We did I don't know, 5 in journals, 22 in conferences, 16 workshops, and 3 book chapters. And there is a bunch of projects that have been already running, like RoboProx, headed by Zdeněk, but in our group by Robert Babuška and Mikuláš Janota, started officially in 2023 already. We still have the ERC-CZ project of Mikuláš Janota. We have a Marie Curie Fellowship by Jonathan Huerta Munive, the Corsens project, and the Formal Ethics project funded by Cisco. We have started in 2024 the ERC-CZ project by Tomáš Mikolov. That's very good, even though the ministry is still making some problems to us. Martin Suda got his own new Gotcha project in machine learning for theorem proving. We are part of the SEDMO funding, and I got a small Amazon research award last year. And in 2025, we will start my XPro project, and a project funded by a company called Novamente in cognitive inference control, and also the Elliot project, where it's headed by Robert Babuška for our department. Some awards that we got you may have noticed that Tomáš Mikolov got the AI award this year. The vampire team represented in our group by Martin Suda and Petra Hozová has won a really big victory in 2024 in the World Championship of Automated Theorem Proving. So they really did an amazing improvement over the last year version, and they basically won almost all of the categories. We got one Best Paper Award. Petra Hozová was a finalist in a PhD award at the TU Vienna. And as I said, I got the Amazon Research Award. We have organized a bunch of conferences, and I will not go into it, and done a bunch of invited talks. Tomáš Mikolov is doing a great job in media appearances. We are doing AI lobbying in Europe and Czech Republic. And also Tomáš Mikolov has a new startup where he's trying to make LLMs for practical use. So that's my introduction. And you will now see 4 papers by the 4 groups at our department. The first talk is going to be given by Jirka Kubalík about the SimFormer.
Good afternoon. My name is Jirka Kubalík, and thank you for the introduction. And I am going to talk about our paper SimFormer end-to-end symbolic regression using transformer-based architecture, which is the result of the work of our group led by Robert Babuška. First, what symbolic regression is. Symbolic regression is a method that automatically generates models as analytic free form formulas. The free form is important. That means that the problem is not just in quotes, it's not just tuning some parameters of formula of some predefined structure. The problem is twofold. First, find the structure of the formula and find the coefficients of the formula. So in the history, there have been many approaches. Historically, the most prevalent method for symbolic regression is genetic programming, which is gradient-free evolutionary optimization approach, which involves a population of candidate expressions. Am I going back or forth? Yeah. Expressions and sampling new expressions by simply exchanging parts of the expression trees between two or more expression trees, or by modifying one expression tree. This method is good at global exploration, but fine-tuning of the coefficients using just the blind genetic operators is challenging. Then there are neural networks. I mean classical feed-forward neural networks, which typically work in a way that they start with some redundant topology and try to optimize the weights of the topology in a way that there are only few active nodes and few active weights in the end, which then represents a simple analytic formula. Thanks to this gradient-based approach, it's good at fine-tuning the coefficients, but on the contrary, but it is not so good at global exploration. It is prone to get stuck in some local structure. An important message is that both approaches start learning from learning the formula. For the new data set, they start learning the formula from scratch. So the inference time is computationally high and computationally demanding. Now we turn to transformer-based approach, which is the topic of our paper. We proposed a transformer that is trained on large collection of formulas to generate mathematical expressions directly from a new set of input-output samples. So the main features of the method are that the training data are not anymore a set of input variable vectors. Instead, the data are tuples composed of dataset samples and the corresponding formula. So we need to somehow pre-process the data before they enter the transformer. We used a set transformer that generates embeddings of the input data samples in such a way that the embedding is invariant to permutation of samples in the data set. Then the important part is that it works in such a way that it jointly predicts the structure of the formula and its coefficients, which differentiates, which distinguishes this method from other methods based on the transformer. We also used an extended encoding method for constants, and we use local gradient optimization, which is optional optimization, which is optional part of the algorithm that optimizes the parameters of the formula. So the advantage of this approach is that once the transformer is trained, then given a new set of data samples, it generates the formula in a matter of seconds, for example. So the inference time is very short compared to the genetic programming and neural network approaches. I have not many. So I will skip those details and go directly to some results, which I believe are interesting. In this work we focused on univariate and bivariate problems. Sorry. I always do it wrong. So there are on the right there are two examples of formulas generated by the transformer given new data set where the ground truth is the blue line and the predicted or generated formula is the I don't know, orange one. So we can see that it is able to pretty nicely generate the correct structure of the formula, and also it fits the coefficients almost and exactly. And the same holds for this example 2D function. There are more results, like our approach is more time efficient than the compared approaches. Our approach also, or the transformer, is able to extrapolate to the data which are sampled outside the training distribution and so on. So many interesting features. Concluding my talk, the advantages of this approach are, as I said, the inference time is very short. The extrapolation capabilities are very good. Disadvantages also. As always, this approach has also disadvantages, and the most significant disadvantage right now is that the number of dimensions and the sampling range are given by the training data set. So what it is trained for, then the best performance is observed on the same problems. So that's it. Yeah. Thank you very much for attention. And if anybody is if anybody is interested in trying this, you can check this GitHub repository and play with the trained transformer.
There must be some kind of knowledge base, like the exponential functions or the functions that the model actually selects as the output. So there are some like predetermined or.
No. All this kind of knowledge is captured by the neural network, by the transformer structure of the neural network. Yeah. So there is no prior knowledge about what should the expression be like if it is given such and such data. All this information, all this knowledge is trained in the training phase, which is, in this case, it took like 33 hours on 8 GPUs A100. And trained on 1,040,000 or 60 on 100 and sorry, I'm confused. Simply a huge number of formulas and data sets. I mean, hundreds of thousands. Yeah.
Thank you.
Okay, so my name is Jan Hula, and I will talk about graph neural networks and language models in the context of reasoning. And the work is based on this paper which is mentioned here. And the motivation for this work is that we would like to come up with a mental model for how to think about language models and other types of graph neural networks. Because I think most of us are excited or surprised by the current models like ChatGPT, and some people even claim that in a few years we will have models which will be able to do research and which will be able to do like design algorithms, but we don't know whether this is possible because we don't understand what these models are doing, and we also don't understand what is required to do things such as research or design of algorithms. And one interesting ability of these models is the ability to do reasoning. And it's also a very dividing topic because some people say very confidently that these models are just memorizing training data or they are detecting some patterns. And some people are very confident that they are already doing reasoning. So we focus on this, but because it's not very well defined, we study it in the context of Boolean satisfiability. And in Boolean satisfiability, you have logical formulas, which is a conjunction of clauses, where each clause could be a disjunction of literals. And literals could be either original variables or negated variables. And we have such solvers which can solve formulas with millions of variables. So we are not trying to compete with such solvers. For us, it's just a domain on which we can study the ability of neural networks. So we study only formulas with up to 100 variables and several hundred constraints, which is already very difficult for humans. Like, for example, humans could not solve such formulas in their head. And before us, there was already a paper which showed that it's possible to train a graph neural network to predict satisfiability of such formulas. And they did it by encoding the formula as a bipartite graph. Work. No. So on one side of the graph, you have literals. On the other side of the graph, you have clauses or the constraints. And then they do message passing, where every round of the message passing, they would update the embeddings of these nodes. And they initialize it by random vectors. And after each round of the message passing, you would update these vectors. And they do 30 passes of message passing. And then they took the embeddings of the variables, and from this they predict whether the formula is satisfiable or not. And they showed it's possible to train it to high accuracy, but there was no explanation why is it possible, why it should work. So we tried to understand this, and we looked at the low-dimensional projections of these embeddings for variables after individual time steps. So each time step could be understood as an application of one layer. So basically, we are visualizing what happens after each layer. And as I said, initially it was initialized randomly, so it's a random point cloud. But if the formula is satisfiable, it will converge to these two nice clusters. And if the formula is not satisfiable, you would have random points. And so this image for us triggered the idea that maybe what these models are doing, they learn to act as a solvers for semi-definite programming relaxation of MaxSat. And MaxSat is an optimization version of SAT, where you try to maximize the number of satisfied clauses. And how you do it, you form maxat as an ILP problem where you have binary constraint which tells you that the variables should be binary, either -1 or +1. And you can design approximation algorithms from that by doing relaxation. So you relax this, instead of optimizing over these binary variables, you optimize over interval from -1 to +1. And this is linear programming relaxation. And once you solve it, you need to round it to the nearest integer, and then you have a solution. And this algorithm will come with a guarantee which tells you that in the worst case, you will not be very far from the optimum. And you can design better approximation algorithms with better guarantees, for example, with semi-infinite programming, where instead of optimizing over this interval, you take these variables, you lift them into vector space. So now you have a unit vector for each variable, and you optimize these vectors instead of the scalars. And so, what you will see if the formula is satisfiable, you will see that the variables would create very nice clusters. So that was our mental model for what these graph neural networks are doing, and then using this mental model, we designed a few tricks. So first thing is that if you believe that the GNN is a solver, you can train it for maybe on few iterations, but then in test time you can increase the number of iterations maybe to much larger number. So we train on 30 iterations, but then in test time we increase it to 1,000 iterations, and suddenly we can solve more difficult problems. And another trick is that originally when you train on everything, it's very hard to train because a long time the model doesn't learn anything. And so we designed a curriculum where we start with small problems, which doesn't require a lot of iterations. And once we reach some accuracy on the small problems, we increase the problem size and also the number of iterations. And in this way, we are able to train it like 7 times faster than training on everything. Then we also do the same thing for transformers, which could be understood as a special type of graph neural network where the graph is represented by the attention matrix, which needs to be trained from data. So this is harder to scale because it's harder to learn, but it's still possible. We are able to train transformers for formulas up to 20 variables. And then you can also generalize it to general constraint satisfaction problems, where instead of having this binary Boolean clauses, you can have generic predicates like, for example, X is brother of Y or Y is bigger than Z. And then you can encode word problems in this language, and you can train transformer to solve it, and you can explain why is it possible. So like on this toy example, we can explain why language models can do reasoning. And that was still a very artificial example. So here is a real example which I took from this paper where somebody asked ChatGPT to write a proof of Euclid prime number theorem, which is at the same time a poem. And you can view it as 2 constraints. One is, proof, and the second is a poem. And the model probably never saw these 2 constraints together in the training data, and it was still able to, synthesize something which satisfies these constraints. And this is much more, of course, difficult because there are a lot of implicit constraints which are not mentioned. For example, that it's grammatically correct and so on. But we hope that our view that we view language models as CSP solvers, that will help us to understand what's going on and also to design better architectures and also drastically reduce the training time, because currently it's probably extremely wasteful how these things are trained. So that's all. Thank you very much. So we have a random generator of problems, and we manage that we make sure that there is no bias. That basically we generate the formulas in such a way that there are always 2 pairs of formulas. One is satisfiable, one is unsatisfiable, and they differ just by one literal. So the model cannot find any superficial statistics in the data, and then we know that we train on large formulas and we sample them randomly, and the number of possible formulas is enormous. So I have a train set of 10,000 dental formulas, and then we have tested which is sampled randomly. So it's very unlikely that we would sample, some similar things which were in the train set. Thank you.
Yeah, thank you. So our next speaker is František Koutenský. So greetings. My name is František Koutenský, and I will be talking about our work called Unlocking Nature Design to Neurocellular Automata. And I presented this paper last year at the Artificial Life Conference. And a disclaimer, this will be more of a fundamental research, but even for you who care about the practicalities, it can turn into it, and it's also beautiful, so we will see. So in nature, the complexity arises from simplicity, like patterns form in clouds, ripples form in sand, and the bacteria, they self-organize into bacterial colonies. There is unfortunately it is not working, but never mind. There was a process of a bacteria growth, and it was described by these partial differential equations. And if one actually examines such a process, like bacterial growth process or some other process, usually the target is to have the partial differential equations, which represents like this deep knowledge about the process. Because once you have it, you can do predictions about the system, and you can do everything, everything about the system. And so it's actually similar to what one of my colleagues presented here before, the SimFormer, I think it was. So it was the idea of doing symbolic regression. So the aim of our work was actually similar. And we also wanted to extract these kind of laws from a snapshot of the studied process. And we aimed to study this kind of biological process that unfortunately you can't really see, but it doesn't matter. So first we had to select the process that we want to study, that we want to use to fine-tune our method on. And naturally, we turned to the master of the pattern in nature. So the dog. No, I'm just kidding. It's the leopard, and there are two reasons for that. The first one is that the patterns on the leopard's skin it's actually beautiful intrinsically, and the second reason, more pragmatic perhaps, is that there is research established around it, and it gave us a basis for our research. So we examine or we use the result of this paper, where the researchers handcrafted models for producing this kind of patterns that actually correspond to the code patterns of the leopard in different stages. It's like 2 days, 8 weeks old leopard and the adult leopard pattern. And what we got, it's these 3 images. It's only thing we got. And our goal now is to train a model that will make the transition from the first pattern, the spots pattern, to the rings pattern, and then to the third pattern, to the rosettes pattern. And while doing that, we also want our model to give us the solution, the PDEs for this kind of process. And to do that, we utilized neurocellular automata. So neurocellular automata, it's like ordinary cellular automata, but with the difference that the rules are now learned by a neural network. And this diagram shows the progression from step 1 to step n+1 for a cell X at the position X. So what we does is, or what the NCA does, the neurocellular automata, is that it applies some predefined filters. It does a convolution operation. So for each filter, we get a perception vector. And once we have these vectors, we can just pass it to some feed-forward neural network. And since all of this is continuous, there is nothing to stop us to use gradient descent to train this method to give us the results we want. And all this is done in a stochastic manner so that the system cannot rely on any global clock. And this is how we trained the NCA model. So as I said, we only had these 3 images provided by the paper that I showed you. And so we start with the spots pattern, and we let the cellular automata to evolve for 30 steps. Then we compare it to the rings pattern, also obtained from the paper that I mentioned. We computed L1 loss, and then we let it evolve further for another 30 steps, and did it again on the rosettes pattern. And once we got these losses, we added them up, and we did backpropagation to adjust the parameters of the neurocellular automata to give us the desired output. And this is, unfortunately, it's a real pity. I can't show you what the transition is that the NCA learned. But you have to trust me, it's really beautiful. Like the transition is really smooth. And just to test out, we only had these 3 images, the spots pattern, the ring pattern, and then the rosette pattern. And the NCA was able to model the transition very smoothly. Unfortunately, you can't see it. But this is not our end goal. We still want to get these equations to have like this understanding of the model. And to do that, I unfortunately don't have time to go in depth with you, but basically we had to adjust the architecture of the NCA. We actually coined the adjusted architecture as DINCA, Dynamic Identification Neurocellular Automata. And basically we did that, we posed some kind of constraints on the weights. The constraint is here. It's only like an example of a constraint. We could pose another constraint as well. But for two variables, we could pose this constraint. And what it tells us is that once we have the weights learned from the model, these are actually those weights that adhere to this law. And one can see that if we apply some clever weight pruning, we have what we wanted. We have the minimal PDE. And so this is what exactly the solution we got for this kind of process. that the model was doing and the equation for it. So a big thank to you for listening, and also a big thanks to the Leopard. Without her, none of this would be possible.
Yeah. Hello. My name is Jan, and I'll be talking about the paper. I'll be presenting the paper that has been accepted to the conference ECAI, and it's about machine learning for quantifier selection in CVC5. So, well, the thing that we are concerned about in this paper is automated theorem proving, and it aims to teach computers how to reason logically, right? This involves like proving statements, like using logical steps. You can think of it like a solving of a complex puzzle where each piece is a logical inference, and it is automated theorem proving in general is important for checking software, verifying hardware, and even for exploring new mathematical complex. And specifically, in this paper, we work with SMT solvers, which are satisfiability modulo theory solvers, and which are specialized tools for automated reasoning. And they are designed to decide on satisfiability of a formula within a certain mathematical logic. They are used for a wide range of applications, from software verification to verification of hardware. But the main challenge for SMT handling is handling of quantifiers, like existential and universal quantifier. And it is usually done by sort of alternation between the ground, something like SMT solver, and an instantiation model. So the ground solver sees the ground formula, and it also says some quantified formulas. It has some instantiation models which suggest some instantiations for the quantified formulas, and then passes them back to the ground solver, and then in this way this continues. So what are quantifiers? In logic, they allow us to express statements about collections of items. Like, for example, here we have that for all x plus 1 is greater than x. SMT solvers handle quantifiers through instantiations, which means that they replace the quantified variable with some concrete values. For example, here we say that it should work for all numbers, so it should also work for some number 0, so we can plug in 0 for the place of x. And now, which quantifiers to instantiate and how? This is the main difficulty of the SMT solvers when they are trying to learn and deal with quantifiers. So what we do, we have the idea that we will use machine learning to intelligently select the sum of the quantifiers. And machine learning is trained to predict quantifiers instantiation, which are good and which are positive and negative. This is the training samples are extracted from previous successful proofs. Each quantified formula is then represented by a numeric feature vector. We train a gradient boosted decision tree to distinguish good and bad quantifiers. Then we implement this method inside a CVC5 SMT solver. CVC5 is a state-of-the-art SMT solver, one of the best currently. And it implements several instantiation models, and each of the instantiation models uses different instantiation techniques, but all of them basically inside they look something like this. They iterate over the quantifiers and then process the quantifiers one by one. So this is the place where we plug in the machine learning. We simply put one if here. So if the quantifier is predicted as positive by the machine learning, then we will process this. And otherwise, we simply skip quantifiers which are considered by the machine learning model as useless. So now I can show you some of the results that we have achieved on a large collection of mathematical problems from Mizar Mathematical Library. So this is just a scatter plot of runtimes. So here we have basically what we want to see is that we want to see dots behind the diagonal, because so we are comparing runtimes of two versions. So we have two runtimes, and we plot for each problem, we plot a dot on that point. So the blue points under the diagonals are actually improvements, right? And then the red joints are actually worsening. So this is what happens when you rerun the same server again. So this is when you just start the same server again without any machine learning, but with a different random scene. And this is what happens. So you see that you lose some problems, but you also get some problems, but it's sort of symmetrical. But with the machine learning, you see that we have much more blue bubbles here under the diagonal. So this is the improvement. So we can see that we have improved, like we have a lot of more problems solved, and there is also the cluster. Those are the problems that are not solved without machine learning, but here with machine learning we can solve them, and there are much less losses, right? And okay, so in the end, achievements. So we have used machine learning to filter quantifiers for instantiations in CVC5. We have nice results of machine learning with machine learning on Mizar mathematical library. We have improved the best strategy by 23%. The best known of portfolio of strategies is a collection of strategies. So we have improved the portfolio by 22%, and this is the state of the art of portfolio. So that's the best current results that you can get from CVC5, and we have improved it by 25%. And we even outperform other ATP methods, which are even ML and H, and should work better with are specified for first topology. There are some future work directions. So thank you. That's everything. That's all. Thank you. Yes, we used to just do very simple bag-of-word features. So we used the number of conjunctions, number of disjunctions in each formula, and things like this, number of quantifiers and things like this.
Thanks for listening to our department's presentation.
On tam měl mobil. Určitě. Já ti dám ten kohot, jo, a ty tam zmačkneš to zelené tlačítko, jo. Aby pak to bude fungovat. To vybereš si, ale prostě vybereš si to, co chceš. And the next speaker is Professor Kuchera from Platforms.
Thank you. Good afternoon. I'm Vladimír Kuchera, and I'm going to report on the research results of the Department of Platforms, abbreviated PLAT. In fact, I am the only member remaining to report the results of this department. The other members have already reported elsewhere. So my results for the last year are here. One article in the IEEE transaction automatic control, which is a D1 journal and one keynote lecture at the International Conference on Informatics in Control, Automation and Robotics held in Porto, and the related paper in the proceedings. I have chosen to tell you more details about the first result, which is the basic research result. Or maybe I should use this. Is it okay?
Oh, you should use it for recording.
Okay. This one. Yeah, okay. So, which is a result of basic research in systems and control theory. And the question is, can the system's zeros be altered by feedback? First, of course, we have to define the systems to be discussed. We consider linear multiple input, multi-input systems of this form, state space equation, where X is the state, U is the input vector, Y is the output vector, A, B, C, D are real matrices. Then the system's eigenvalues, including their multiplicities, is specified by the elementary divisors of the matrix A minus Si. This is a well-known result. The finite zeros of the system are specified by the finite elementary divisors of this matrix, sigma. And the system's zero at infinity, or S equal to infinity, including its multiplicities, it's specified by the infinite elementary divisors of this matrix. So this means that the eigenvalues, zeros, finite or infinite, are in fact part of the Kronecker invariants of this matrix sigma. Now, to modify systems properties, we use feedback. And the most powerful feedback is state feedback, which includes the entire state X. The form of the feedback is U is Fx plus GV, where V is a new reference input. And now it's important to distinguish regular and non-regular feedback. If the matrix G is square and non-singular, the feedback is said to be regular. Otherwise, it is non-regular. So non-regular means typically G is either tall or fat matrix, but not square. Then the resulting closed-loop system is given by these equations, and usually in control applications, it is required to be stable, meaning that all eigenvalues of the A plus BF matrix having negative real parts. Now, the first claim is that regular state feedback can alter poles, but not zeros. Assuming the system is controllable, its eigenvalues can be modified at will using regular state feedback. In particular, the system can be stabilized, for example. But the zeros, however, cannot be altered. They are invariant with respect to the regular state feedback. So if you see, this is the state, this is the sigma matrix for the closed loop system, and this is the one for the original system, and they are related by a non-singular transformation, provided G is non-singular. So they have the same invariance. So zeros cannot be changed at all by feedback which is regular. Especially difficult are zeros, and they are critical to achieving the desired performance. Even in stable systems, unstable zeros, called non-minimum phase zeros, may result in an initial undershoot. See, the red one curve. This is a very undesirable behavior. For example, just imagine an fictitious airline company called the non-minimum phase airlines, whose flights always start first in the wrong direction. And the result of the paper is that zeros can be modified, but only by non-regular state feedback, which is more powerful. The paper presents necessary and sufficient condition for a pre-specified set of zeros to be assignable by state feedback. And the result is that new zeros of any value, finite or infinite, can be added. But the existing zeros remain always in place. Only their multiplicities can be increased. And the increase always comes from the unobservable part of the system, which is a part of the system dynamics, which can be controlled, but it cannot be observed. And the role of the non-regular state feedback is to connect it to the system in such a way as to achieve the goal. But caution, non-regular state feedback can destroy the system's stability, even stabilizability, while modifying its zeros. It can destroy almost everything. So we must stabilize the system first, and then authorize only stability-preserving state feedback to ensure stability. And the question arises, it is useful at all to add zeros? Oh, yes, it is. For example, in system decoupling. The task of decoupling is to eliminate the couplings which exist within the system using state feedback, so that each output is influenced by one input. So here, okay, the coupling is 2, and this one is to be eliminated. So how to do it? Simply, the idea is to subtract -2 here, but first we must create a box like this here. And this is the zero to be added. Here is how we create a copy of the coupling and how it can be subtracted from the origin. So in black, it's the original system. It has one integrator here, which is not observable, but controllable. So we use it to create a box like that, having 0 at +1. This is done by the red couplings here. And when we had such a block, which is exactly the same as here, we connect it to the input U1. So now we have a copy of this coupling here. And we subtract it. That's it. So we created an additional 0, which is a copy of the existing ones, with the aim of eliminating an unwanted coupling. Decoupling is useful. It has been successfully applied, among others, to eliminate the couplings, for example, between the active front and rear wheels of a 4-wheel steering vehicle to achieve yaw stability, overturning, or to design active vibration isolation tables and suppress internal interactions in a precise platform positioning, or to control the top pressure in a blast furnace for the presence of strong couplings between the top pressure and the top gas cleaning and recovery system of the furnace. There are other applications in the literature. So, thank you for your attention. That's all.
So, any questions? Systems? No, sorry for that. That's all. That's all. Thank you very much. And the next talk will be given by Tomáš Juchman.
Okay, good afternoon. My name is Tomáš Juchman, and I'm presenting results of Recap Testbed Prague. So first of all, I would like to mention 7 conference papers. One of them A star, 2 of them A, and 3 will be ranked this year. Between other results, I can mention a functional sample, 2 verified technologies, and software. One of those software we are getting ready for licensing this year. We also contributed 2 or 3 chapters in Professor Mařík's book. Those were additive manufacturing and digital twin chapters. We also made some contribution on an industrial conference, Siemens Realize Life, between one of the largest companies in Europe. And also, I think that it is good to mention that thanks to the long-term cooperation with our partner Continental AG, they were capable to get Global Lighthouse Network Award, which is top 170 companies in the world, which are using like the most high-tech technologies, artificial intelligence, and so on. And for starting for the next month, we are also getting cooperation with Mateo Company, which is manufacturer of robotic like extruders from metal. So based on this cooperation, we will be capable to deploy these solutions to end customers and companies. And now I would like to give word to my colleague Víceman. And sorry, here are some illustrations of the results.
Okay, hello, my name is Víceman. Today I will be presenting one of our work on object pose estimation using implicit representation for transparent object. Why we do this is because as part of flexible production line, we want to introduce new objects into robotic manipulation pipeline as soon as possible. One crucial part of this manipulation pipeline is 6D pose estimation. That is where the object is located in space and how it is oriented, so it is able to be picked up by a robot. Furthermore, due to the costs and time savings, we also are looking into using only a single RGB camera, and we would like to have generalized method which doesn't need to retraining on any specific object. Furthermore, in this work, we focused on transparent objects, which are one of the harder objects to manipulate due to their non-Lambertian behavior, due to the reflexiveness and transmission. This we tackled using implicit representation, more specifically neural radiance fields. The representation of a new object, due to these benchmarks with other methods, we did partially synthetically, where in simulation we applied different shaders, extracted the images, and used instant NGP for getting the representation of the object. This training takes around 2 minutes. Then we use this representation but we basically adjusted Megapose render and compare pipeline, where we replaced the initial mesh rendering with this rendering from instant NGP, which we believe that the photorealistic behavior of instant NGP and neural fields increases the precision. Furthermore, we also fine-tuned this network to be able to work with these nerves. As I said, custom fine-tuned dataset, it is also created synthetically. We then evaluated on 4 dataset, varied datasets, which included both classical objects and transparent objects as HouseCAD, under which are more only transparent object with varied backgrounds, and then even some industrial metal objects. We used multiple metrics listed here for evaluation. So our results are highly positive. We observed that even without needing for retraining, in certain cases, just implementing the rendering increased the results of this method, while for the fine-tuning increased it only in case of transparent object, but that is to be expected. We lost some generality. Okay. This is basically a visualization because the numbers are nice, but as you can see, this is projection of the estimation in the space of the different objects. In green, you can see the ground truth. In orange, this is just replacing the rendering, and the purple is for the fine-tuning. Just to be mention it once more, we only use a single 2D image at the input. So, in conclusion, another part, we don't only need to necessarily have the items scanned from simulation, so we can just retrieve this implicit representation from the image, which you can see in the from set of sparse images, which you can see downwards in the bottom. Furthermore, our method does not require any retraining for specific objects. The render and compare works without it. We validated also our results on multiple data sets. Our next part of research is actually deploying this pipeline into like real robotic manipulation. So that will be all for me. Thank you for your attention. If you have any questions.
Okay, is just sorry, but I would like to just at the end short word about the cooperation, because this is the purpose of this day, I guess. So we have a really good infrastructure in testbed thanks to CIIRC project, and it is possible to be used by you. So do not hesitate to come to testbed, ask for some robots you would like to use for your experiments or some other devices. So that's everything from me.
Thank you very much. Thank you for the offer. And now we will have a break. So since we are slightly behind the schedule, we should meet here at 14:40, right? 10 minutes later than scheduled. Okay, 14:40. And you can go for something to eat for Respirium, because there are still some reminders from the lunch. So don't hesitate to go there, and copy is behind the door, right? 14:40 sharp here, so that we can start the next talks.
My máme Vaška Křemena v Americe, chtěli poslední prezentaci.
No,
je to nějaká
funguje nám tady ten smysl.
Nenahrál video, nebo?
On říkal, že bude online právě.
Já ho nevidím jednak. Tak se připojí na ten. No, co to někdo vidíte? Já bych to měl být přihlášený. Kam se? Jsem levo dole. Tady řeknu ty, jo? Já.
Jakož prezentace budou o tom ode mě.
No, to je super, ale s tím...
Já jsem nevím, no.
Já jsem tam při...
Já právě, no.
Máme na
jsem to pochopila.
Já taky máš.
Připojený takový.
Jo. Že vlastně ono by tady trošičku mohlo tohle. Já teďka nevím, co Omlouvám se, ale měli to být všichni jako...
Já vím, no, těžko přijede.
To chápu, jo, ale to s tím by tam měl být.
Pohodě, no. Nejde to.
Zkusíte, prosím vás, to šerování, jestli dostanete. Musíte dát zelený tlačítko.
Já musím to našerovat.
On se tam asi někdo nepodepisoval.
Pan profesor Kučera.
Ten to dělá poctivě, ale...
Jo.
To se nebude vykazovat ještě jako že tady obecně to jsem včera.
Nemáme fotku.
Oh, jasně.
Ale to je v rámci...
Nebo můžu to letos hodně, no. Jo, takže to můžu prostě použít. Jo.
Já jsem tady před 2 minutami ještě prezentoval, tak jsem se ještě spočil na záchod.
Tak
Ne, v pohodě, nic. Takže úplně, v pohodě. Jo. Jo, super. Jo, super. Jsi úplně první? Jo, super. Jo. Tohle funguje. Je rád tady to je. Hele, já to mám tak na 7 minut, jo, tak to nemám nic. No, já si myslím, že taky.
Jo, Michalka jsem stepal ještě, jo. Tak je straně, jo. Teď už to
Jo, on říkal, že má časovou baterii.
Takže jsem řekl, že určitě budu rád, když mě to minimálně přečte a takovéhle věci. No, právě. A ráno odjel a už se to vrátil.
Já jim řekl, aby se sedne, jo. Vy to máte sešlet, jo? So sit down, please. We should continue. Okay, so now we will have a block of presentations from two departments. One is Cognitive Systems and Neurosciences, led by Lenka, and another one is Biomedical Engineering and Assistive Technologies, led by Olga. So please, Olga.
Good afternoon, ladies and gentlemen. Well, let me introduce to you the leader of the first group or department. It is Cognitive Systems Department, and here is the leader or the chair of the department, Lenka Alhocka. My name is Olga Stepankova, and I will be talking about the BEAT department. We have decided to join both presentations because we have very close cooperation, and the main kick for deeper cooperation came from the recently awarded project CLARA, what is Horizon European project led by colleague Shivitz, but one of the work packages is being well conducted in our both departments. So we are trying to join our forces as much as possible. So the first department, namely the COCSYS systems, is consisting from quite a few people, as you can see here. This represents 10 full-time equivalents. So only part of the people are really in full-time job, while the others are partly cooperating or working in some hospitals or research institutes dedicated to medical domain. Namely, this is the case of the group, well, named Neuroinformatics of Normal and Pathophysical Hearing Functions, who cooperate with the department, thanks to the fact that there is a great laboratory for hearing problems, which is established in this institute. We should review all the projects on which we are working. There are 3 international projects which are being conducted in the department, namely the newly started CLARA project, plus 2 smaller projects in context of Erasmus or Interreg. This or the last year, the department decided to somehow push the cooperation with practical life and try to transfer much more the results of previous research into something real, which can be handed out to society. That's why we are very happy that this trend is being supported by 3 edicts, which are ending this year, and we hope to be able to talk or present the results during the next meeting we will have in a year. Besides, the people at the department are working on 2 grants of the Agency for Medical Research and on 2 grants of the Technical Agency. The grants I have referred to produced quite a lot of interesting papers. The best ones are named here because they are in the top journals, and the others, well, are interesting, but they need to. That's why we have decided to conduct or well, introduce in the second part of this talk to live presentations. One will be dedicated to of the promising directions. It will be given by Jan Hlubik, and the other presentation will be given by our colleague who is currently in United States, and we hope he will be able to talk about our role in the CLARA project. Now, let me introduce briefly the second department, namely the Biomedical Engineering and Assistive Technologies. This department is, has the review of some projects on the right side. It is important to mention that we are also cooperating in the domain of CLARA, and besides, we have some other research which is dedicated to AI utilization as a reinforcement tool for learning and improvement of learning results of university, which was dedicated or gained from technical agency. Here you can see the list of people. We are just 4 people working in the department, but we have some PhD students which are cooperating with us. And here we have decided to invite for the presentation here 2 people who are co-authors of very important papers which appeared in D1 and Q1 journals. So it will be Milan Němý and Michal Huptych. I'd like to mention that Milan Němý is currently cooperating or starting cooperation in a grant agency with the military hospital, and the first result of in the direction which will be given to this project or this grant will be presented here. It is worth of mentioning that it is a sort of another type of transfer of results from one domain to the other, because here he is applying some basic ideas which have been used also in his PhD thesis, and for which he gained a prize from the Alzheimer Research Fund in the last year. So let me pass the floor to my colleagues, and the first one will be Milan.
Right. Good morning. Good afternoon, everyone. Okay, so once again, my name is Milan Němý, and I'm a postdoc researcher here in the BEAT group. And today I'd like to talk about the results of our research on the non-invasive description of brain tumors using MRI, magnetic resonance imaging. And it is collaboration mainly with Military University Hospital and also Karolinska Institute in Sweden. So first, to give you some background, so I'll be talking about gliomas, which are type of brain tumors. They are very much aggressive, so there's high need to really address them. So we can characterize them into 2 different ways. One way is something called grading. Tumors can be either low grade or high grade. It really means that they are either slowly growing or very aggressive. And that's important, because then we can really choose and decide on the course of the treatment and surgery, for example. This is very nice, and we know lots about it. The problem is that to know about if the tumor is high grade or low grade, we need to do a biopsy. So we need to take out a piece of brain tumor out of the brain and really put it under the microscope and then see how these cells look like. So that basically means that it's like another surgery before the main surgery. And then the newest trend is finding out about gene mutations, because these brain tumors can have different gene mutations. There's like one which is called ADH gene, which is nowadays the most, or what we know is the most important gene to really predict the growth and development of the tumor. And again, this can be decided on the brain biopsy. So we need to take out, again, a piece of the brain of the tumor, of the actual tumor. We cannot simply tell that from like the blood analysis or cerebrospinal fluid analysis. We need really piece of brain to tell. So it's pretty invasive. It comes with problems, of course. So that there's always like needs to do this non-invasively to really tell. And we know these two, grading and gene mutations, are really descriptive, and they can tell us a lot about if we should operate, not operate, what the treatment should be. Yeah, but this puts a heavy burden on the patient. Yeah. So for this, it's possible to use MRI, which is of course non-invasive technique. Most of the patients can be scanned. Of course, it can also be a problem in some cases, but usually this is pretty fine. We already have some techniques. Yeah, we already have some techniques such as apparent diffusion coefficient model or diffusion cortices imaging, which are just some ways to look into the brain using MRI, and usually it's by looking at the diffusion of water molecules in the brain. The problem is that these methods weren't developed focused on the tumors, and so they basically look at the direction of the fibers, the brain fibers on the axons. And the problem is that the glioma cells aren't really affecting the axons. So usually when we look at these existing methods, they will tell us maybe something wrong, but maybe more in severe cases which are non-operable. So they are not really designed to do this, but it's like the only option which we have so far. So for this, we propose a new technique which is called spherical mean technique. It's been used already in multiple sclerosis, but not here. So we use it in this case also, and we designed the whole pipeline, how to like set up the MRI machines, like for the MRI sequences, how to pre-process the imaging data, and then how to use this technique. How it works in a nutshell is that it can really model separately the axons and then the tissue which is outside the axons. So we can really see what's happening in the tumor, not in the axons which are going through the tumor, which are not affected by it. So that's really good. And what we can see in the image in the right bottom corner is actually, so on the right side, that kind of remind us really like the brain and the directions which are going there. And that's actually the axons. That's like the older technology, let's say. And on the left side, that's really something which tells about like the underlying processes, not the axons. That's what we need. In the paper which we published in American Journal of Neuroradiology, we showed that this actually can be used here and is superior to these standard measures. For this is just like a preliminary study where we needed to first segment the tumor from non-tumorous tissue in the images by hand. So this was done by medical experts. And then we looked and investigated the diffusion properties and had like different indices. And so what we can see in the table is that, so what's called FA, that's fractional anisotropy, that's like the older measure, and then we can see, and that's what the doctors, what they can read. They know sensitivity, specificity, AUC. That's why we show these like very simple linear measures. So that's not very ideal. However, medical experts use this. And you can see it's definitely not ideal. Sensitivity 50%, specificity 82, AUC around the midline. So that's not very good. But then the second part of the table, these are all the measures from the spherical mean technique, and we show that there are some which are really superior. And actually, in the paper, we showed like the whole pipeline, how to set up the whole protocol and give really like tutorial for the doctors to use this. And we showed that it's really possible. Because that's why this is important. We kind of know this method before, but it wasn't used in this kind of cohort, and there wasn't any like a prescription for the doctors to know like how to really go step by step and show some working prototype. Next to this, we also published this review in the neuroscience and biobehavior reviews. And yeah, there's another thing, but I didn't present it here because it's just like a review paper. And I also would like to mention that for the paper I presented here last year, I was awarded Dr. Jan Bureš Award for the best scientific publication in neuroscience, and also got Junior Faculty Award from the Alzheimer's and Parkinson's disease conference. And also I'll be continuing doing this research for another 5 years as I got a Junior Star grant from the Czech Science Foundation. Right. Thank you very much.
Thank you. Any questions, please? Last question. So the objective is to capture many disease diagnosis or
I wouldn't say it's diagnosis. We know that they already have tumor, but it's one of like the biomarkers, like reliable biomarker, which can predict how the tumor will like behave in the future, and what kind of treatment we should use, because it's directly connected to it.
Thank you. And the next talk will be given by Michal Hupty, right?
So, good afternoon, everyone. My name is Michal Hupty, and I'm going to present our last paper based on the Prague of OHCA clinical trial, which is called the time-dependent yield of invasive versus standard resuscitation strategy. This paper is based on idea of Dr. Brian Grunow from the Department of Emergency Medicine at the University of British Columbia. And we had the opportunity to collaborate in this idea with him. So how I said, this is based on the Prague OHCA randomized clinical trial, which is I was at clinical trial where the data was collected from the 2013 to 2020, and the main purpose of this trial was to test two approaches of the treatment during the cardiac arrest. So it means two approach for resuscitation, some standard approach, and invasive approach where is used a specific device, Lucas, and some specific assessment. And the main important thing is the ECMO, extracorporeal membrane oxygenation, which is out-of-body blood oxygenation device, and it's very important here. The study has 256 patients, 132 in the standard and 122 in the invasive arm. And the primary outcome of the study was the good neurological outcome at the 30 and 90 days after randomization. And we know from the previous analysis that the cardiopulmonary resuscitation time or long or duration is so very important, especially for the selection which kind of approach of the resuscitation we should use, especially if we have a long cardiopulmonary resuscitation longer than 45 minutes. We know that it's significantly favored for the invasive approach of the resuscitation. And we also know that in the invasive strategy and invasive approach, there are more accurate the favorable neurological outcome, especially 30-day favorable neurological outcome is significantly more accurate in the invasive strategy resuscitation. So now we have some session, and now the main purpose of this study, of this paper, was to prepare or to perform a secondary analysis of the PRAC-OHCA data in order to demonstrate the phases of benefit and time-dependent prognosis for the invasive and standard resuscitation strategy. Here we have the first description, we can say first result. You can see two distributions or two graph with the distributions of the in the left figure of the numbers of probants or patients with the good neurological outcome at the 80-day from the randomization. And on the right picture, you can see the proportion of the good neurological outcome. And both the pictures are in the 5 minutes epoch based on the duration of the resuscitation. And if we want to interpret the left figure, you can see that the blue, dark blue bar are patients or probants with exclusively conventional resuscitation. It means without ECMO, without Lucas, standard resuscitation during the cardiac arrest. And you can see that there are relatively steep decline of the numbers of the patients with the good neurological outcome, while for the probants with the invasive approach of the resuscitation, there are first phase from the, let's say, 10 minutes up to 40 minutes, where we can see some one first way of the people with the good favorable outcome or the favorable neurological outcome. And then from the 40, probably 45 minutes up to 80 minutes, we can see the second wave of these people with the good neurological outcome. But these one are saved by ECMO, because this is using of the ECMO what make this this result. Of course, if we can compare it in the proportion, we can say again that the conventional resuscitation is again a relatively steep decline during the first hour, but the invasive arm and the ECPR treatment are relatively stable, and for all epochs, for the whole time, there are some stable band between the 11 and 35% of probants with a good neurological outcome. This is a very good result, very good promising result, but it's an approach which is called intention to treat. It means it's according to the randomization in the study during the according to the protocol.
And there are problems that in the clinical research, we have some problems with the crossovers. And sometimes it's necessary to switch from one arm to the second arm and so on. And it's not clear how we want. Therefore, we prepared some second view where we use very simple calculation, where for each minute interval, we just use these two equations. In the numerator is number of pulseless probands or pulseless patients with good neurological outcome at given minute, and in the denominator is total number of pulseless probands at the given minute. And if we prepare this and create the graph based on this calculation, we obtain this description, and it's very powerful because here you can see the power of the invasive from the invasive approach of the resuscitation immediately. And of course, you can see here very clearly the second window of opportunity to save the life of the patient with the cardiac arrest, while the standard approach is almost reached the 0% of life or patient with good neurological outcome. So thank you for your attention. If you have any question, please. A Lucas device and mainly the ECMO. Yeah, this the extracorporeal membrane oxygenation then. Yeah. Yeah, that's the invasive is mainly the name is mainly because the ECMO. But the Lucas, it's you can see the device here, and it's very powerful for the cardiopulmonary resuscitation, and it's also, of course, no invasive, but not so easy.
Sometimes destroying patient.
Yeah.
Sometimes destroying patient.
Just, of course.
Okay, thank you very much. The next talk will be given by Mr. Ruby.
Thank you very much. Good afternoon, ladies and gentlemen. I would like to present our ongoing study to assess hydration in geriatric patients by bioimpedance, namely BIS, bioimpedance spectroscopy. So basically, what is our motivation? Our motivation is the fact that the hydration plays a very important role in NAH. And basically, dehydration is the most common cause of fluid electrolyte imbalance in older patients, and also the major problem in hospital admissions with these elderly people or elderly patients. The problem is that the dehydration is a complex phenomenon with no exact simple definition, which is the problem because the standard characteristic is a plasma urea-creatinine ratio that is derived from blood samples that have to be measured or taken by educated nurse, and then those samples have to be delivered to laboratory and assessed. So it takes a lot of time. It has to be done by educated personnel, and also it's invasive. Overall, there is no light and handy method for estimation of a human hydration. So we are trying, or what we are trying to do is to use BIS electrical parameters of human body to assess hydration, and mainly to correlate it with plasma urea-creatinine ratio. And hopefully, with those electric parameters, we will be able to compare it and get a hydration of the patients. So in this pilot study, it's ongoing study, and this is basically the first results. We had 13 geriatric patients from age range 71 to 92 years old. So you see the patients were quite older. And the protocol was that after taking blood samples, by educated nurse and that were sent to Unilab's laboratories. We made BIS measurements, and we were measuring all BIS raw data. So we were measuring all electrical parameters of the body on all frequencies. And we are using Bodystat 5000. Basically, what we are trying to do, we are trying to compare those data with biochemical parameters. And first of all, we were using 50 kilohertz phase angle, which is most commonly used by doctors these days. And then we were also using nutrition index obtained by this. That's basically the first step for us to show it to doctors, something that they know that is more common, and then we will be following up with the directly measured electrical parameters. So you see there's just a brief overview of obtained results, and you can see the phase angles are quite low, which is typical for elderly people or sick people. Here we can see the phase angle versus urea and phase angle versus creatinine. We were calculating correlations with creatinine and then a nutrition index with creatinine, and the correlations were 0.68 and 0.61. Basically, what we are trying to solve, we are trying to use directly measured parameters, because these days these devices that are connected with body composition are normally using calculated parameters such as total body water, intracellular water, extracellular water, and those parameters are calculated by regression equations. So as you know, every regression equations gets some biases into results. So we are trying to overcome these problems or these biases by measuring direct electric parameters, which are shown here on the next slide. These parameters are Cole diagrams, which is basically reactance versus resistance on whole frequency spectrum, which is basically direct electric parameters of body. And we hope that we will be able to use these parameters to describe electrical parameters of the body and to compare those measured parameters directly. You can also see that every Cole diagram has elevated left side, which is typical for elderly people or for old people. Also, you can see that Cole diagrams, it is for every person we measured, is basically on a different place, and this is due to the body type and body shape of the patient. So overall, in the spinal study, we were able to obtain a correlation of 0.69 between phase angle on 50 kilohertz. And as I said, we were using phase angle because it's most commonly used by doctors and they know what they are basically, what basically does it mean. Then you saw the typical left side elevated Cole diagrams for elderly people, which we hope that with more patients we will be able to describe briefly more. Then we were able to show some further correlations with nutrition indexes. And as I said, it's an ongoing research. And because it's work with live patients, with elderly people, it's not always easy to get blood samples and the measurements. Basically, we are doing the research at the geriatric clinic. So it has to click, so not every patient can be measured. But till today, we were able to measure 42 more patients. So we get approximately 55 patients, and the research is still going. So hopefully at the end of the first quarter, we will be around 60 or 62 patients. And after that, we will be able to assess it once again, and we will be able to use directly measured electrical parameters that might be able or might be better for description of hydration status of the patient, and we will be able to figure out new, very easy, non-invasive method for estimation of body composition / hydration of the elderly people, which might be very useful and helpful. Thank you very much.
Try to connect someone, right? But I'm not sure if it will go. Of course, please go ahead. This bioimpedance spectrum basically bioimpedance. It's measured current and this method is using two electrodes or electrode model. So you are basically using on the whole spectrum. You are using on the right side of the body. Electrodes on the feet and on the thank you very much.
Can you hear me, guys?
Yes, please speak louder.
Speak louder. Okay. I have headphones. I don't know.
Wait a minute, please. Wait a minute.
Sure.
Please try it now.
Is it better?
Yeah, it's better. It's fine. Thank you.
Perfect. Can I share the talk?
Yeah, please touch the share button. The green button.
Yeah, I got it. But,
Confirm.
okay, I gotta allow the screen sharing for Zoom. I will just reconnect real quick. Give me a 30 seconds, okay?
Okay, we are waiting, but please go fast. Yes. Once more.
Yep. Is it good now? Can you hear me?
I hear you, but you have to share the screen.
Yeah. I will do it. I just needed to allow it in my system settings. I'm on different computer here, so it should be there now.
It works. Yeah. You are live.
Can you see it?
We see your calendar.
Calendar?
Your slide. Yeah, it works. Go ahead.
Okay. Sounds good. Perfect. Okay. Can I start?
Yes, you have like 10 minutes.
Perfect. Thanks much for having me. Good afternoon in Prague to everyone. I will talk on the series of stuff that you guys will see probably few more is from me now, but I'll just pick up one paper that we presented today, and both all these things will be on using artificial intelligence and machine learning in brain implant devices that people use chronically at home, on daily basis. They got implanted and then go home and use the device for several years. So I'll show you some interesting results and data. This is my disclosures. from last year. So this is our little CIIRC team that work on this paper that I'll be talking about today. Vlad Sladký, my PhD student at CIIRC, and me. So talking about the new brain technologies, I'll just do the comprehensive, quick, brief review here. We are trying to design the next generation devices that helps with epilepsy management or other diseases like Parkinson or psychiatric diseases. This what I'm showing today is the epilepsy use case, and that's essentially the device that's implanted in the chest of the people, tunneled the electrodes and essentially through the burr holes in the skull, plugged electrodes in the targets in the brain, deeper brain structures like temporal lobe here. And this particular device has capability of sensing, continuous sensing. So we stream the data 24/7. We build the interface, the whole platform that streams the data out of the device from the people when they live their normal lives. We can test their memory score. We can look how many seizures they have. And we build a whole platform that integrates all the data from variable sensors, implantable devices, and so on, to aggregate it in the cloud and run the distributed cloud computing to get the results from the data and maybe find some biomarkers that help us to optimize the treatment, which will hopefully enable physicians to use better, more optimal treatment for the human patients in future next 5 years, 5-10 years, hopefully. We'll see how it goes. So today I will talk about one particular paper that's very interesting because the device also has capability of measuring the impedance. So we build in the system where we measure impedance every 30 seconds, or recently, or we were doing it every 15 minutes for a long period of time. Long period, I mean like months and years, where the device is implanted in patients. So it's interesting to observe the impedance changes. This paper was published in Journal of Neural Engineering, and main author was Richard Cui from our team at Mayo Clinic. So what is it? I hope you guys will like it because this is engineering stuff, impedance, and that brings me back to undergrad studies. So this is how the device looks like on the panel A, and this is on the panel B. It's a CT of co-registered electrodes. You can kind of see where the electrodes are in the brain here, in the two targets on both sides, and then this is the sketch of how the electrodes looks like in the tissue. And what we essentially measure with these contacts, which are pretty apart, it's like a 0.5 millimeter space between the contacts, so it covers a big area in the brain, essentially millions of neurons. So what we think it measures actually is the extracellular fluid changes and extracellular impedance changes during the time that you are measuring it. So it can be in the order of hours to catch the circadian rhythms of the brain cellular fluid not exchanges, or it can be months to see if there are any long-term changes, maybe caused by seizures and stuff like that. And we did some measurements in beads. This paper also compares it to this saline measurement in a benchtop experiment, just to make sure that what we are measuring is correct. So the device is a simple device. It's not like a spectrograph or something like that, where you can swipe the frequencies from 0 to kilohertz. It only has essentially a measurement tool that ramps up the pulse in like 80 microseconds, and at the very end it measures the voltage. That's what's standardly called impedance in this area. So it's really just the real U over I ratio. And but what we did is testing if you measure that what does this compare to if you measure it by spectrograph? So usually it compares to measuring impedance at around 2 kilohertz. You can kind of see it here on this graph. So what is interesting is that we could measure the impedance from the implant for several days right after the implant, which was never done before in human. We got 5 subjects where we measured this, and you can kind of see this type of curve for everyone. So you see the parabolic and exponential kind of curve where the impedance right after implant goes slightly down in first few days, 1-2 days, and then it slowly exponentially ramps up to the stable condition, stable level, and you can measure half-life of it and all parameters of this. So this is how it looks like. I just want to show you the gray stuff. You can kind of see how it oscillates. I'll look at it later. This is the daily oscillation of impedance. So on this bigger curve, you can see that there are daily cycles where the impedance changes during the sleep mostly and during the day on pretty regular way. This is how it looks like for essentially almost all patients. This is one patient, all electrodes that we were measuring it. The device had 16 electrodes, so you can kind of see it's kind of similar curve on each electrode. So the other important thing for the stimulation therapies for brain stimulation is how the impedance and things like that changes when you start to stimulate the brain. So what we were testing in this paper was how does it work compared to saline, which is the red line, where there is no brain. So if you stimulate, you just keep getting the same impedance of saline because nothing is changing. But in the brain, if you start stimulating, the impedances goes down, and if you stop stimulating, the impedances recovers back within like 7 days here. So sorry, 7 hours here. And if you start stimulating, it goes again back down. So and you see kind of magnitude, order of magnitude in which it changes, and you like to see that and know that when you're starting to treat the biomarkers and find the biomarkers from brain diseases, how these biomarkers can just change based on how the impedances of sensing electrodes are changing when you stimulate. So this is an important thing. And this is how it looks like if you start stimulating at the very beginning after implant. Then about like 100 days, 150 days, the whole tissue makes long-term changes, and then it essentially settles on the same value of impedance, and from like 200 to 60 days, it won't change by the stimulation itself anymore. And so there are some long-term changes in the brain when you start stimulate, which essentially copies the days for the big studies with the stimulation devices that are showing the effectivity and outcomes of these devices for epilepsy that are measured usually after half a year from the implant, because before that you see the fluctuation of outcomes really. So the brain really learns something in here based on how you stimulate. And the other thing that we show in this paper is based on Philip Miewald's paper that was published last year, 2 years ago, where he showed the cycles of impedance changes during sleep. Here you can see the hypnogram, and you can see that people during the day, impedance essentially grows up, and then during sleep, it recovers back down, especially during non-REM sleep. So you can kind of see the fluctuation between non-REM and REM dreaming sleep phases, where the impedances goes back up a little bit and down, and through the night it recovers down to 0, and then the other day continues back up. So it builds up, like the sleep pleasure builds up. So in this paper with Richard, we were checking how these cycles are stable over a long period of time, like 602 years essentially, or a long time, and you can kind of see that they are stable all the time. They oscillate within these amplitude changes, but the oscillation doesn't go anywhere different. It kind of stays in the same level. And this is the thalamic target. This is the hippocampal amygdala target. So it's even in different structures of the brain. So what to take from this? It was an interesting study, which was never done before in human. Measured the impedance long time like this, and check how it can influences the therapy and the sensing capabilities of finding biomarkers and optimizing therapy. And what we found is that the minimum value is essentially after implant reaching in 2 days, which is related to scarring, to bleeding, and then it starts scarring of the tissue around the amplitude and around the electrode, and the impedance is going back up in essentially like 2 weeks or 2-3 weeks, and then it stays, when the tissue is scarred and recovered around the electrode, and then it stays kind of stable. But then it decreases also with the impedance changes, with the stimulation, and then we saw the phase and the amplitude of the oscillations. The circadian rhythm of oscillations are stable over hundreds of days. So these are like main takeaways. And also this is all stable in different anatomical locations, whether you are in thalamus or hippocampus or post-hippocampal targets. So this is very useful for delivering the stimulation, finding and optimizing the stimulation for next neuromodulation devices that will enable sensing, for example. We share everything. You can find most of the things you can find on these 2 links here if you are interested to look up more. So this is it. Thanks for attention, and I'm open to questions if there are any questions.
So that was the last speech. Thank you very much for coming, and I hope that this colloquium will help us increase collaboration and that we will understand each other better than before. Okay, thank you. The session closed. There is some food left or not? We don't know, maybe. Bye-bye, Václav.
See you. Thank you, Zdenk. Thanks much.